We are both from ESA, the Earth Science Division in ESTEC. This morning we have 4 presentations on 4 future missions. We will give you an overview of those missions. Well, let's start straight with the first one, which is Rose L, and Julia will present it.
Thank you, Christian, and good morning, everyone. My name is Julia Kubanek, and I'm part of the science team developing the ROSE-L mission, together with my colleagues Malcolm Davidson and Lorenzo Giannini. But there are many more people involved in the mission development, such as Nuno, whom most of you know very well, but also the project team in ESA and ESTEC, but also many people in industry and around. So I will give an update about the mission objectives and science status and where we are currently at with the mission. So I start with the Copernicus star timeline. I think also this one many people have seen already. So what is ROSE-L going to do? With ROSE-L, we focus on filling observation gaps, so to provide new information which is not yet available with our current fleet of Sentinel missions. Enhanced continuity is another aspect where we improve current observations in terms of accuracy, quality in general, and temporal and spatial resolution. For ROSE-L, we are currently in phase D, targeting like a launch in 2030-ish. This slide shows the different services that currently rely on the Sentinel-1 data. So there are different services looking into sea ice type, concentration, ice sheets, glaciers, snow water, but also going to ocean surface wind vectors, ocean surface currents, looking into the land use change, soil moisture, forest biomass, deformation, snow water equivalent, flooded areas, iceberg detection, also for vessel detection and maneuvering, and oil spill location and morphology. So the ROSE-L mission will also look to addressing the needs of these user services. So there are different expert groups, different policy documents, and together with Sentinel-1 and Sentinel-1 Next Generation, we are looking to address all these new user needs. And for this, we have like the so-called mission requirements document that is guiding every of our mission developments, in which we summarize all the mission requirements with also justifications that it's really mapping the user community needs. A bit about L-band and scene depth, scene visibility. So the longer wavelengths of L-band is sensitive to larger and more stable scene features. And compared to C-band, shorter wavelength, 5.5 centimeter, which is more sensitive to displacement from superficial or unstable features. I have a few examples here. Looking into water below canopy, where you can see in the top image the data here from ALOS and here from Sentinel-1 compared, and you can nicely see that there are different patterns visible in the data. Also for sensing motion in vegetated areas, you can nicely see different deformation patterns detected in C and L-band here in the red areas. But the blue area here is only detectable in L-band. And we have seen this yesterday also in presentations focusing on NISA. And then also sea ice. Again, we have here ALOS 2 and then Sentinel-1. And for sea ice, we have had like a good study looking in the synergies of both data sources, where sea and L-band can nicely be used together to complement each other, as different ice types are visible. But for instance, also icebergs are much better visible in L-band than in C-band. So we are looking here into the application needs and mission requirements. So we are targeting an improved resolution of 50 square meter in the so-called ROSE-L interferometric white space mode, RIWS mode. We look into providing information at a 0.25 to 0.5 hectare resolution for agriculture and forestry, high resolution soil moisture products, and also for maritime applications, this resolution is meaningful for iceberg and vessel detection. We are targeting a low noise of smaller or equal to -28 dB. for sea ice mapping, which I just showed an example of, and marine and maritime applications, but also to support soil moisture products and flood detection and area mapping. Then repeat pass is similar to Sentinel-1, so a 6-day with 2 satellites, 12-day with 1 satellite. Here also addressing the interferometric applications, so surface deformation, land ice velocity, and snow water equivalent. Revisit is quite high. It's 1 day in the Arctic, 3 days in Europe, 6 days global. For sea ice monitoring support, geohazards, so flooding, landslide, and active tectonics, but also for soil moisture measurements and seasonal land monitoring, so such as snow water equivalent estimations. We also support wide swath imaging over open oceans for mapping extreme wind events such as hurricanes and cyclones. You can see like many of the applications of Sentinel-1 are appearing here also for ROSE-L. A bit about the mission in brief. So the consortium is led by Thales Alenia Space in Italy, involving 29 companies from 15 different countries. The mission will consist of a constellation of 2 wide-looking satellites, so the pre-flight model and the flight model 2, and the design is enhancing synergies with Sentinel-1, so we will fly in the same orbit with collocated swath on the ground. We are currently in phase D. I said this in the beginning, so the system critical design review was declared successful in June last year, with all top technological risks retired. That's a very important step in our development, and the spacecraft is built afterwards, and the QAR scheduled in late 2029, so that's then before launch. Instrument-wise, we have an L-band with the ITU allocated band. We have a planar active array antenna of 11 by 3.6 meters. We use a score and elevation and maps and azimuth. Also there we had some presentations looking into it yesterday. With 5 digital channels downlinked and combined then later on ground. And the main mode I mentioned is this ROSE-L interferometric wide swath mode, so similar also to Sentinel-1, with a Scanza duopole 50 meter square resolution. A bit more looking into the SAR modes. So we have on the left side the baseline modes. A bit more detail about this ROSE-L interferometric wide swath mode. So it's Scanza, covers 260 kilometers swath, 5 by 10 meter ground range versus azimuth resolution, and the noise I mentioned. Then we also have quad-pole capabilities, covering like an incidence angle range from 25 to 42 degrees, same swath width, and 5 by 20 meter resolution on ground, same noise. Then we have a ROSE-L wave mode. Access will be variable, 20 by 20 kilometer vignettes with a spacing in between of 100 kilometers. Ground versus azimuth resolution is 5 by 10 and also same noise. We're also looking into an optional mode, so the ROSE-L extra wide swath mode, which would be bigger than 400 kilometers with a resolution of 20 by 40 meters and a noise smaller than minus 30 dBs. The reason for this is that we would like to maintain operational flexibility, also like when only one of the satellites is up or if like one of the satellites would fail. But also, I mean, it's like many years from now, also to respond to the evolving user needs, which you may not know now, but which may come up in the future. But it's really like an optional mode for now and could support hurricane wind field detection and tracking. Then I would like to look a bit more into the design synergies with Sentinel-1. So we are in ESA really looking a bit into a system of system paradigm and enhanced information and services. So we try to meet the services evolving different requirements in coverage, sampling, time series, and coordinated with Sentinel-1 and ROSE-L data streams, which will be collocated in space. So we have the same orbit configuration and the same ground track of Sentinel-1. Main mode will be dual pole, guarantees full swath overlap with the Sentinel-1 interferometric wide swath mode on the ground. The acquisition plan will be expected to be a superset of the acquisition plan of Sentinel-1, and all active Sentinel-1 tracks will be matched by the corresponding ROSE-L tracks. We have an orbit duty cycle of about 38 minutes per orbit and 10 terabyte downlink per day, so which is about 5 or even bigger than 5 times that of what we are having with Sentinel-1 now. The mission design at this moment supports 2 phasing options. That's not decided yet, but there can be the opportunity to fly in different orbit phasing, so that we have 1 Sentinel and then 3 days ROSE-L, 6 days the other Sentinel, 9 days ROSE-L, or that we fly in a convoy. This is a topic that will have to be addressed with both missions, so Sentinel-1, NG, and ROSE-L, and we will address this based on the user needs and will be discussed in the mission advisory groups. Yeah, we have a few examples here for the joint access with Sentinel-1 and optimized revisit configuration. So this 3-day baseline with the interferometric white swath and ROSE-L interferometric white swath mode. So it would be the average access capability smaller than 1 day for latitudes over 50 degrees. And then for the Mediterranean Sea, average revisit 1 to 1.5 days, from 2 to 3 days with a single system, and the maximum revisit 1 to 2.5 days, from 3.5 to 5.5 days. So there would be a very nice improvement. And you can see it also in the simulations we did here with a phasing of only ROSE-L, the average revisit on top and maximum revisit below, and then also in the constellation where we have Sentinel-1 first generation and ROSE-L in this 3, 6, 9 day, what I just explained, and how the average revisit and the maximum revisit change. And then we also looked on different places on Earth how the data would be able to be provided then, but it's just based on simulations now, and what I said, the decision is not yet made. Then we also the mission development is guided by a science support plan. So in this science plan, we address the user needs, development of products, and study things we don't know yet. So it's really to tackle mission trade-offs and mature science readiness levels. And we have some ongoing activities. One is a study on ionospheric mitigation algorithms. We also heard yesterday ionosphere is a really big problem in L-band data. So we are really trying to review mitigation requirements and verify algorithm performance, and also to design processing strategies for near real-time products and higher latency offline product reprocessing. So that's a study currently running, and we hope to get a better insight into the ionosphere and how we can deal with it. Then we have studies, 2 studies on model and algorithm for ocean products, because it's also a quite new topic, to consolidate the L-band GMF MTF models, so the ocean models, and to verify quality achievable by ROSE-L white swath and wave mode configurations. Then we are also doing airborne and ground-based campaigns. So this Agri-ROSE-L campaign was a very big campaign that took place last year with DLR's FSAR system, where we flew during an entire growing cycle every 6 days, so to map what ROSE-L will see, about 3 months long, to really get a nice data set of L-band. And we would like to use this data set to make a trade-off between better revisit versus quad pool data. So we have dual pool and quad pool, and there will be analysis following. There will be a presentation on this campaign on Wednesday in the Future SAR missions and concepts. And another comment I would like to make, it was not a campaign only serving ROSE-L, but also other Copernicus missions such as CHIME. We had, in addition to the FSAR flying every 6 days, another airplane flying with a high-specs instrument. We have had a really big ground team doing all the in-situ measurements, and we had Check Globe flying too. So it's a really nice campaign data set, also looking into hyperspectral data that will be available soon. Then also something I would like to mention, there were some ideas to look into the ROSE-L friendliness. So there was the option discussed to have a third flight model for ROSE-L, but that one retired at the CDR. But the option for the sync link for phase synchronization was then not exercised. but the objectives requiring cross-track and the long-track companion formation would not drive the ROSE-L mission requirements. But still, we started looking into it now because the system can be used for companion flying, and we started different ESA studies. So 2 are focusing on the science, where we really look into a ROSE-L companion satellite infrastructure for cross-track and the long-track, and really also looking into this gap filling, which additional products would be provided by a companion satellite to ROSE-L. And then at the same time to these 2 science studies, we are also looking into the implementation we just started a call for the pre-phase 0 study ideas on instrument level. Okay, let's summarize very quickly. I know I'm a bit like over time, but I'm also giving the next presentation, which will be a bit shorter, so I think we covered that, I think, nicely. So ESA Industry and the European Commission are preparing the Copernicus expansion mission in L-band to close critical information gaps and to strengthen current Sentinel capabilities for Europe. And we are really addressing the 2 missions as a system of systems. So combining C and L-band, I think it's really important. Also there, we saw yesterday a presentation on combining different wavelengths. We can really look into synergies and how the systems could be used side by side. And that's also how we target the development. We have a few things to deal with where we need to study a bit more in the future, such as what I mentioned, ionospheric effects, level 1 calibration challenges, big amounts of data, and also we still need like different models and algorithms for some of the priority applications, for instance, maritime surveillance. We also work together with other space agencies, so we have a good collaboration with JAXA, and we are getting ALOS-2 and soon also ALOS-4 data that are used in our studies to better understand the L-band signals, of course with JPL and NISA, and also with SAOCOM we have observers also in the mission advisory groups. That's all from my side on this mission. Thank you.
Thank you, Julia. Any questions?
Thank you, Julia, for your presentation. So will ROSE-L have a side L-band to calculate the dispersive phase, just like that of NISAR?
Sorry, I didn't understand the question, and I don't know who is asking. Sorry.
Yeah.
Okay, thank you.
Again, the question?
Yep.
So will ROSE-L have a separate L-band sideband to calculate the dispersive phase, just like that of NISAR?
No, I don't think so. The systems are different.
So it will be based on a standard split spectrum for removing the ionospheric signature?
There is, sorry, yes, yeah.
Okay, thanks.
Yeah.
I have a question too. So, thanks for this presentation. It gives a really great overview of what ROSE-L can do. And you mentioned also very clearly that there's also quad-pole parametric capability. My question is a little bit, is there a strategy how to use it? Because in the moment, as we know, the dual pole is a standard observation. Is there a plan how to use quad-pole?
I think that's, at the moment there's no plan how to use quad-pole, but we will have the capabilities. The study we are doing based on the campaign data set from your campaign will help in identifying this. But I can imagine there might be like selected areas where we use quad-pole, but it's something really to be decided and defined in the mission advisory group and discussed with the users. But like looking into like, that's like why this trade-off between coverage or like where is it and quad-pole information is very important, and I think it will be a very important study to do in the near future.
No more questions?
Here's one in the front.
Here.
I just following Irene's question. Is it any technical or practical obstacles that we can do, for example, a quad pole instead of dual pole for standard acquisition mode?
Yeah, I think the problem is what you may have seen like in the ground track. So the you have like a smaller swath for the quad pole, and then you have like a lower revisit, and that's like why generally it's like the dual pol used, but that's why we want to do this study to trade off for certain areas. If like quad pol really delivers more information, that we should use it over several areas. Yeah, but usually I think more users are interested in a higher revisit than in the quad pol information.
Thank you. You said the data amount is 5 times higher than Sentinel-1. I didn't quite get that. Can you explain why is that? Is it due to resolution, not quad pol, or swath width, or?
I'm not too much in the technical aspects, but it's like, I think the antenna is like really big, and I think it's from the resolution combined with the swath width and from this maps acquisitions. But maybe I... Sorry? Yeah, it's maps, right? Yeah, yeah.
Okay. Thank you.
Yeah.
Hello, I'm curious with the mission readiness.
Thank you. It's really difficult.
And community involvement of ROSE-L. So, how can an independent research groups and academic institution actively prepare for the contribute to the calibration and validation of phases of the ROSE-L mission?
It will be similar to all other missions that we are having, that at a certain point calibration will be prepared with our colleagues in ESRIN, and then there will be calls for studies, and where everybody could basically apply to. And also now, I mean, there are several activities running, such as like the Sentinel user preparation studies, and like there are many open ITTs where everybody can submit, if based in Europe, obviously, to study data uptake.
Thank you.
Thank you. We can move to the next mission. Julia will present Sentinel-1 Next Generation.
Okay, yeah, as I said, it's, this presentation will be a bit shorter because we go hand in hand with ROSE-L. Also here we are working with the same science teams, colleagues in ESA, but the project team is different. And we had a new project manager taking over from Ramon Torres last year, Thibaut de Koopman, who's now responsible for the Sentinel-1 Next Generation developments. And also here there are many more people behind in ESA and around who are supporting this, so it's just like a few names for really big projects with many people behind. Also here, same slide with a timeline, and now focusing on Sentinel-1 Next Generation. The mission will mainly focus on continuity. So continuity meaning that all services and applications that are currently depending on Sentinel-1 FG, you will see in my presentation more because we call it first generation internally, and the continuous provision of the C-band and spaceborne data at the base of the user-level information products, so level 2 or higher, what is really used by the services. The performance of Sentinel-1 NG is therefore defined that it should be as good as the performance of the first generation or higher in terms of all mission characteristics, so imaging performance and revisit and latency. And also the continuity in data provision should be ensured during a time of periods of mixed operations. So when we have still Sentinel-1 first generation running and are taking up with Sentinel-1 next generation, that also in this time of overlap, the users and the services can still continue to use data and provide their services. Then, also similar to ROSE-L, we are looking here into an enhanced continuity. So also the mission should address like the needs of services by responding to new areas of development and or evolution of services, because we are looking like more into the 2034 time frame, and also the user requirements may change over time. Then also here, again, similar to ROSE-L, we are also looking at observation gaps, which Sentinel-1 NG might be able to fill with a better performance compared to the first generation, and that cannot be provided currently by first generation, but this should not imperil the overall continuity requirement. So that's really the overall requirement of the Sentinel-1 next generation mission. Again, like the same slide, I don't want to go into detail here, but it's again like the same services uptaking the data and where we use in this system of system together with ROSE-L to feed the services and ensure that we match the requirements in the mission requirements documents together with the mission advisory groups. Some looks into the next generation imaging. We are looking into an enhanced spatial resolution. We are targeting to provide information for smaller parcels, especially within Europe. So looking into 0.5 hectare parcels, which are mentioned in the European Commission working document. And you can nicely see, like on the top, it's data from the Acquisa campaign, so quite longer ago campaign, where we have Sentinel-1 interferometric wide source mode compared to the strip map mode, which would equal more the Sentinel-1 next generation, where you can nicely see what a different resolution could do. Then we would like to improve the detection of flooded areas with the enhanced spatial resolution, provide a better offset tracking for land ice monitoring and estimated number of looks for snow monitoring to result in the end in a better product accuracy on different levels, and then also to detect an increased number of persistent scatterers or distributed scatterers per unit area and to improve the information content. And I think like this images that we put here is quite interesting and underlining how resolution helps in detecting PS or scatterers. So in the first one we have like the spotlight, here the strip map image of Terrasa X, and here Sentinel interferometric wide source mode image, and you can nicely see how the number of scatterers decreases in these different data resolutions. Then also higher resolution will improve sea ice ridge detection, which will present also important information for tactical navigation. We will try to detect smaller vessels and infrastructures such as speedboats, looking into trafficking, smuggling, piracy, fisheries control, and also to improve our oil spill and iceberg detection algorithms. Then the next one, first was resolution, now it's enhanced revisit, also going a bit into the questions we had before. The enhanced global revisit of 3 days to capture large-scale flood events, that's like a target. Then also enhanced global revisit for strong impact on soil moisture and seasonal snow monitoring, and the revisit of 0.5 days to 1 day for monitoring of sea ice in the Arctic. Here's a simulation down with a constellation of 2 satellites if you compare different swath widths. That's compared from first generation 250 meter compared to 400 kilometer. And you can nicely see in this average revisit in the days how this 1 day line in Europe is like really moving down with a bigger swath width, but it's just a simulation here. Then looking into the continuity and enhanced continuity, the requirement to support systematic acquisition, so really similar and following up on Sentinel-1. We are looking into a minimization of number of acquisition modes to build up consistent data series, so really in line what we are currently doing. The enhanced continuity is given by improved performance, building on new technological developments, by maintaining all mission elements of Sentinel-1 first generation. So it shouldn't like imperil what we are doing service-wise. We are looking into an improved main dual pole wide source mode, into a quad pole capability in addition to the operational dual pole. And then enhanced wave mode and also a dedicated polar mode in answer of user needs and requirements to support monitoring of the complete Arctic, which is responding to the challenges identified in the integrated EU Arctic policy. And this should be used seasonally. And then we will have an enhanced AIS payload with capabilities to receive messages also in the new data exchange system bands. Then also here we are looking into a maps-based antenna architecture, which will enable ATI for enhanced detection of small or generally vessels under challenging sea state conditions, and also in ice-infested waters and estimation also of the velocity of these vessels. And we are looking into an enhanced ocean surface current velocity estimation. a bit a look into the system of system in brief, because I thought it's nice to compare like first generation ROSE-L and next generation. So the constellation of all these missions is always 2 satellites in the same sun-synchronous orbit, such as of Sentinel-1 first generation. So also Sentinel-1 next generation will share the same orbit. And with 1 satellite, we have the 12-day repeat cycle, and with 2 satellites, we go to the 6 days. We have like the different modes here. You see for Sentinel-1 next generation, we are supporting 400 kilometers swath and supporting 25 meter square resolution, but that's to be like studied and traded off now in the phases to come. But I think it's nicely like visible how these systems could work together in the future and the different parameters. And particularly if you compare here the revisit and coverage from Sentinel-1 first generation and to next generation, how we will improve to 0.5 days in the Arctic, 3 days global, closing the North Pole gap, as I said on the slide before, and also with a much higher duty cycle of up to 43 minutes per orbit. And like the enhanced AIS, which we are also like flying the AIS now on Sentinel-1 CND, but that's even like with the enhanced bands. Then, like a bit like looking into Sentinel-1 first generation legacy mode that was studied, that had different reasons, because we would like to support the cross calibration between the first generation and the next generation, and to demonstrate of full level 2 continuity during the Sentinel-1 NG commissioning, that we can really have a smooth transition from one system to the next. But it's also providing a backup for Earth Explorer 10 Harmony if Harmony extends beyond Sentinel-1 C or D operation, because the system has changed so much that it could not just fly with Sentinel-1 next generation, so it requires a specific mode. This legacy mode will be based on the hardware required for the operational mode, but it will not drive the design of Sentinel-1 next generation. So it will be there, but it shouldn't like impact our developments. And also Harmony, so also here we are working like across projects with the other missions. We'll implement compatibility with the Sentinel-1 next generation legacy mode, so that they would be able to fly with us if they have issues with the first generations, or if their lifetime is longer than expected. And also here, Harmony can then be used as a to study bistatic applications, etc. Also like similar to ROSE-L and for the future to come. A bit about the procurement and status. I don't want to go into detail here, but what I would like to say is that the contract was awarded to a consortium led by Thales Alenia Space in Italy for the spacecraft, and with Airbus for the SAR instrument prime. That happened very recently, and the phase B2 started after successful negotiations on 8 May 26, so really only a month ago. The formal contract was signed last week in Aula, so we are really going ahead now. It's a really interesting time, because we are trading off these mission requirements with the system drivers, and the system preliminary design review, which is like the end of this phase B2, is scheduled for end 28, and the qualification acceptance review for the first spacecraft is targeted for 2034. Yeah, again, like some conclusions and future outlooks. So ESA is working like really together with industry and the European Commission in preparing the next generation of the Sentinels and the evolution of the system. So looking into the continuity of the first generation, but also to enhance existing applications and to enable new applications. So we are really looking into this target continuity, but being open to really also advance, building on the improved performance and observation gaps. Yes, some technological developments. We have a highly performant imaging targeting 25 square meters, minus 26 dB noise, and support of 400 kilometers swath capability. That's under study currently, what will be achieved. And industry will present the optimized SAR mode options by the end of 26. And then we will also have a clearer picture what the system will be able to deliver. This will also be discussed with a mission advisory group that's guiding our mission development, and and also based on this, there will be like a science support plan, such as for ROSE-L, which will like map down what we need to study in the future and how we need to prepare for the mission, that we understand all parameters very well. Thank you.
Thank you, Julia. Questions?
Hi, thank you for the presentation. I have a question regarding the snow pictures. Can it be used for avalanche prediction or anything, or this is just the general avalanche prediction in mountains?
I think in areas, yeah, but I would give this question to the snow experts maybe, but yes, yeah, it can. It like depends on the acquisition geometry in the mountains, right?
Okay, thank you.
But it's also like looking into the hydrology of the areas and seasonal melt, etc. Yeah.
But is it foreseen at all? Is considered, or this is just the general picture from satellite that we have some area covered with snow and some not, and some with
no.
Like
there are services that are using the data in like snow areas for different things, like how rivers are fed, like dry snow, wet snow. So that's really happening, and there are many like data being produced from Sentinel-1 first generation. Yeah.
Further questions? One in the middle.
So I don't fully understand all of the different observation modes. So I have quite maybe a simple question, which is that if you have the ScanSAR modes here, and you were talking about a Sentinel-1 first generation legacy mode, how compatible is the old observed, like the first generation data of Sentinel-1 with the planned observations from the next generation? Can you see them as a continuous series of collected data, and how well will you be able to match those two together, given they seem to be different in some aspects?
Yeah, it's like a bit, I think it's like two questions in one. Like, one is like this legacy mode is only a mode developed for cross-calibration between the systems, but it will not be the main mode used, because then we wouldn't achieve like the higher performance, and we would stay like with Sentinel-1 first generation. But but it could be enabled, for instance, over oceans to support harmony if there's a need for it. But it will not like imperil what we are doing in like the usual observation in the monitoring perspective. And the other question is more from like going from Sentinel-1 first generation to next generation. There are like really discussions how we will do this on the science side, but that's something we will ensure, and that will be part of the science plan I mentioned in the end. For instance, like we are discussing in the mission advisory group for deformation time series, how long do we need an overlap between the system that we can really continue feeding the European Ground Motion Service with the data coming from Sentinel-1 next generation. I hope that answered your question. Good. Maybe we should move on.
Good. So thank you, Julia.
Okay, yeah, thank you, everybody. With this, I'd like to introduce our next speaker. So going from the legacy mode, talking about harmony, to the harmony mission given by Paco Lopez-Decker.
Thanks, Julia. And this is the only presentation in the session not given by ESA. Björn, who works for ESA, should have given this one, but he didn't want to come. So I'll give a bit of a harmony talk, and it's always hard. I guess most of you are harmony aware by now. So it's, for most of you, it will be a lot of repetition. Some of you are new, so for you it will be new. And then I'll try to give you a bit of status. Okay. I like this picture because it shows a bit where we are. Yeah? So a few years ago, we had a nice idea, and we were saying we will have small satellites, enhancing what you can do with Sentinel-1, and then things moved. And now we have pictures of how the satellites are going to look, which for me is very nice because I can show them. It also shows that the satellites are not small satellites to go to where Sentinel-1. They're actually big beasts. Still small compared to Sentinel-1 in terms of weight and resources needed, but these are major satellites. So 13 meters in length, end-to-end. It's actually longer than the Sentinel-1 antenna. 1.2 tons per satellite. That's comparable to biomass in terms of mass, but 2 of them. So it's a major effort to put this in space and to get a lot of performance. You can also see in the foreground, you see the antennas. And you see it's a bit of a strange antenna architecture with holes. This is not because we wanted to save money, but because we wanted to get performance out of this. And the antennas in the end are giving you ATI capabilities, like they were discussed a bit yesterday. But Mario in the first session about Sentinel-1. And then we end up with this quite complex antenna system. It will do digital beamforming and some maps like Sentinel-1 XG and like Roselle will do. And we'll try many of these things. Okay, so I like the satellites. I hope you like them too. As you know, or maybe not, it's a multi-domain Earth system mission. I spent most of my time on the first part, looking at upper oceans and Earth-sea interactions. Today I will focus on the other parts because the community sitting here is more interested in land and in tectonic strains and things like this. So I will not talk about the oceans, although it's actually a very nice part of the mission. But it's a multi-domain mission, which makes it hard because we are developing lots of things at the algorithmic point of view. There are many mission drivers driving the mission design and the specs, etc. So the concept, if you don't know it, so we start with Sentinel-1, which was missing from the picture. I always show the picture, and I was a bit sad that I cannot show Sentinel-1 with that, and this has to do with copyright and things like this, so we cannot put the Copernicus satellite in our Earth Explorer picture, which is a pity because it's about half the mission. It's a transmitter plus one of the receivers, so we really need Sentinel-1 to do its job, and Sentinel-1 does about half of what you need. So it transmits and then it receives. I like to tell people that radars are extremely inefficient machines because you send a lot of power and you get very little back. So it's always a good idea to put more receivers to get a bit more signal back with more properties. So that's what they're doing. So we are putting 2 more receivers in different places. And because you are INSAR people, you immediately know what you get out of it. So you get line of sight diversity, so you get sensitivity to motion in different directions. And in other contexts, I would have to explain this, but for you, for sure, I don't need to do that. And I'm also highlighting one of the main things that you are going to get out of Harmony, which is the ability to get deformation in 3D. So to fill the missing gap, because we are mostly sensitive to the deformation, combining ascending and descending. And with Harmony, we will get the third dimension. And then we do all kinds of other things, which I will quickly mention because they're still cool. So we are going to look at the Doppler over the oceans to get the surface currents out of it. We will use the backscatter over the ocean or the multistatic scatter over the ocean to get winds with high resolution. We will look at ocean waves. We added a bunch of thermal infrared cameras, so we have a complicated system with five cameras in each satellite. So if you have a use for thermal infrared imaging that you can link to your whatever you are doing, then let us know, because we may then turn them on over land as well. But this is intended for the oceans, and we can use them to look at clouds and the motion of the clouds, the position of the clouds. So that's kind of cool stuff. And we have a formation flying system, and that's nice because it gives you freedom in where you put the satellite. So we can move one of the Harmony satellites from being very far away. Yes, they are spaced about 700 kilometers from each other and 350 kilometers from Sentinel-1. But you can move them, and then you can go to something that you also are very familiar with, because you have had years of presentations about TandemX. And we are doing sort of the same. And so we will fly during part of the mission, the two satellites in close formation at less than a kilometer distance to form a single pass interferometer, which is conceived to generate the digital elevation models. And then we are interested mainly in ice, in the loss of ice, or maybe the gain of ice, if you are surprised. And also in rapid changes of elevations related to volcanism and things like this. And I also like to do ocean topography, but that's not the topic for today. We have some requirements, we have some mission goals and some requirements. There is a few slides of those, but I'm only showing the ones that are relevant for the community that is here today. So for land ice, and we want to look at topography change, and we are targeting about 2 meters, so 20 centimeters per year in sensitivity. And here we're talking about very large signals. We're talking about meters per year of height variation, which you cannot follow doing repeat pass interferometry because you're looking at things that they correlate. So there is an exercise in generating time series of additional elevation models and subtracting them from each other. We're also looking at ice flows, like Thomas Nagler was showing yesterday, but now with the added line of sight diversity, so that you also there can get a 3D motion of the ice without having to make the assumption that the ice is flowing in the tangential direction to the glacier or things like this, which you have to do right now. And here we target 5% of the motion speed as our goal. And then over land, the usual numbers, so we want to do repeat pass interferometry, but then with the added line of sight diversity, and we are getting, we hope to get, and in the simulations we get to about 1 millimeter per year in all directions, where the one that we add is actually as good, or if not better, than the other ones that we already had. So that's the goal, and also what we think we are going to get at some resolution. Resolution is a bit a misnomer in this case because it's most of it will be PSI, so it's whatever permanent scatterers you have will dictate what you get. But also you can do it over distributed areas. And then also over land, we want to look at sudden topography change, in particular for volcanoes, where also the signal can be huge. It can be talk about hundreds of meters of change in a very short time span. And we want to be able to measure that. There is a very old mission timeline, which makes sense in the sense that we will launch the 2 satellites at once, so they will start in a close formation phase to do cross-stack interferometry. That makes sense from a science point of view, because we want to see how topography is changing over time, and the more time you have between the observations, the better you are able to get rates of the formation. So we launch in a close formation. We start with probably a year of close formation, single pass interferometry, and then we will move to this stereo phase, more line of sight diverse, more sensitive to motion, and then at some point we will go back to this close formation phase. There is enough propellant on board to actually add additional short cross-track interferometry phases during the mission, but it is something that needs to be optimized. So there will be a bit of a dance of the satellites during the mission to alternate phases, and this will be optimized as we go, as it usually happens. Now we'll go a bit over some of the products and to illustrate what we're doing, and also the work that we're doing right now. So we of course, the entry product for you will be the SLCs. Now, we gave a bit of a strange name to the SLCs because we have this complex system with multiple antennas, and we can decide to process each antenna individually, which is something we will do over the oceans because we want to do along-track interferometry within the different channels. But for you, you're going to be interested in the best image you can get out of the system, and this will be these SLCs, which we call combined phase center, where we do digital beamforming to get the best possible quality, and that's what we will be using. We will co-register the SLCs. This is already going to happen at some point for Sentinel-1, and it's also the idea, as far as I understand it, for Roselle. For sure, we will do it for Harmony. Where the Sentinel-1 team not do it for Sentinel-1, we will do it also for the Sentinel-1 data that coincides with the Harmony data, because we want to deliver to people an easy-to-process data set. And this is relevant for Harmony because getting data properly co-registered in a quite difficult bistatic geometry is non-trivial, so we want to facilitate this step by doing it already. And this co-registered SLCs, we will have them both for the single-pass interferometric data sets, but also for the time series. And then we have this COF product, which is a bit like the GRD that you have now, but for all the systems and polarimetric. So we will not only look at the backscatter or the multistatic scatter average at something, but we will also look at the covariance between the two polarizations, which has a lot of information, at least in the bistatic case. This is a complicated slide trying to illustrate how we go towards the co-registered SLCs. If you look at it with a bit of passion, you will identify all the things that you already know about. So it's not super innovative, except that the steps are complicated because of the bistatic geometry, so there are some challenges. We have to account for, so when you position something, you have to go through your bistatic range equation and consider the range-dependent Doppler. There's a lot of variation in Doppler in the slide. You have to do things like the ramping, which you also have to do already with TOPS data, but with much larger Doppler centroids, which means that you have to do it better than you have to do it right now. And then there are phase biases and things like this when you do spectral diversity, where you also have to consider the geometry that you have. Maybe a note, which I think is important, we will have an ETAT layer, and this ETAT layer is specific for each of the satellites because we are looking at the atmosphere in different geometries, so you are seeing a different, you're seeing different effects. Single pass interferograms. This is a very silly slide because all of you understand what a single pass interferogram is, but I use it to illustrate where we are in the development of the tools. So we have a very complete end-to-end suite that can generate synthetic data and go all the way to the processing of the synthetic data. So we have, these are simulated data, simulated images, and you can do pairs of images. And then we are going through the effort of registering and doing all the processing as if they were real images to generate your interferogram with way too many cycles, which you can flatten using the assumed topography, and from there you can go to the final product, which in this case would be a digital elevation model. You have seen this many times before because we have seen tandem mix for years. What's nice about this one is that it's a large DM because Sentinel-1 produces large images, and the other thing that's nice is that you can do many of those because Sentinel-1 provides a lot of imaging capabilities. And that's the new thing that we get with respect to tandem X, for example, and the ability to get dense time series of digital elevation models, and from there go to topography change or time series of topography if you are interested in that. And then we will go for deformation. Each time series of tracks of harmony is going to give you two components of the motion, one in the one that you already have with Sentinel-1, the one in the line of sight direction of the satellite, more or less in the zero Doppler of Sentinel-1, and an along track component. And the along track component comes from the fact that you have several line of sights, and if you consider the two harmonies and in your head, you can probably do it. If you have an along track deformation, it will give opposite sign signals in the forward and backward looking harmony. So when you subtract the two, more or less, that you get the difference. And the nice thing of that is that most of the atmosphere goes away. And so we know that when we do repeat pass interferometry, the performance bottleneck is the atmosphere, but for the along track component, most of it goes away, which makes us very sensitive to motion, despite the fact that the line of sight diversity that we have is finite. But the big issue is actually being removed, and this is also why, in fact, that component tends to be quite good in our performance analysis. This is a bit of programmatic thing for you. We are developing tools, and we want to give the community something that they can use to process the data and also use it ourselves or use it in the ground segment to generate, to process the data. So there is an effort to make a derivative of stamps in Python, which is working to some extent. And you can ask Andy Hooper, which I guess is around, for more details. And then there is a specific version, more research-oriented of that. So we have stamps and PyStamps as the Python version, but there is a second line of development, which is the StampPy, which is not specific for harmony. So it's really a research tool, but with the adaptations required to handle harmony data. So in principle, this will be available for people to play with if you have no better option. And then from the time series of components, we can go to 3D deformation. This illustrates, what this illustrates, in fact, is that you get the north-south component very well, which typically would be missing in this case. And if I were to show performance plots, I would illustrate what I said before, that in this case, the north-south, the uncertainty in the north-south component is as small as the uncertainty in the other two components. And then a couple of slides to finish. Very programmatic. We have this big suite of simulation tools end-to-end to model what you care about in this room today, I think. It's evolving, gaining complexity, but it's already quite complete. And if you want to know more about that effort, then please stay until Friday, because there will be a presentation about that in the Harmony session, not by me, so much better. There's lots of ATBDs. I think that for most of the things that we're discussing, we know how to do it, and with me I mean you. So I think that if we were to give you Harmony data tomorrow, there's plenty of people in this room who would be able to figure out how to deal with it, because we are doing things that we have been doing for years, with the difficulty that everything is multi-static, and the geometry is a bit difficult, so there's still some scratching your heads to do. But these are things that are going to work. We have processors in place. Probably the processing will be based on GAFA. If you want to know about GAFA, find Ingvar, who is around as well. We have a mature chain for 3D deformation, which I think is going to work quite well. We have a baseline approach for everything above eyes. There is a bedrock processor in place to generate DMs based on these EO tools, which are open source. There is a validation strategy study just started, which covers all the goals of Harmony, also the ones I'm not showing, which is quite challenging. And if you are interested in developing operational processors, then stay tuned, because I guess sometime soon there will be an ITT out for the development of the operational processors that should start somewhere next year, but it is still being defined. But at some point it will come, because we need to be ready to play with the data in 29, where the mission is still planned to be launched. A very nice thing about Harmony, if you have my position in the world, is that since we depend on Sentinel-1, which is typically seen as a problem, it means that we really need to run and be there in time. Everybody knows, everybody's working towards that, and I think that's a luxury position to be in, because we have seen that most of our other Earth explorers are delayed by things in the order of a decade. But this is not going to happen with Harmony, because we need to fly with the transmitter. System CDR, so SAR CDR is starting soon. System CDR will start at the end of the year, so it will be finished somewhere in the first quarter of 27, I guess. And then, as I said, launch is still planned for 29. Still, the baseline is to launch on Aviga C, but we will see. And that's it. Yeah.
Thank you, Paco. Are there questions? Any questions for Harmony? Oh, there's one up there.
Thank you for the presentation. I was wondering, you showed the digital surface model, but seems like it's not one of the target product, just like something that is produced on the way. I was wondering if what is the expected quality for it, and yeah, mostly if can be used in also alone.
Sea ice? Yeah. The question was about sea ice?
The digital surface, the DM.
So they are one of the targets, and the quality of digital, that depends on where you are. So over land, we are targeting something sub-meter in terms of your height, with a resolution of 50 to 100 meters, and this depends in the end on how much you can average. So if you can average, so if something is static and you can average over time, you can get as much performance as you want. Over ice, one of the biggest uncertainties is penetration. So you have to get an accurate DSM, then you need to know where you are, how deep you are below the ice, and that's a bit the limit. But we are also targeting sub-meter performance in height. Is that an answer to your question?
More or less, yes.
More or less. That's always the problem. People ask and people respond something different, yes.
Okay, are there any other questions?
Just one quick question. If the mission went beyond 5 years, would you kind of keep doing the same kind of plan for switching between topography and deformation?
I don't know. And I think, so what I would hope, what I personally hope, is that first that it happens, that the mission gets extended and satellites have a long life, and that it becomes a difficult question, because that would mean there is lots of people like you asking for different things, and you want people to really want it and then be in a conflict situation. I would imagine that extending the deformation time series is probably the most, is what I would do right now. So I would go for that, go for line of sight diversity, to extend 3D deformation, because I think this in the long term is the application that will bring the highest value. It's not the most interesting from my point of view, from a science point of view, from a development point of view, but from an application point of view, I think it's the most useful. So I would imagine we would do this. But if other people come with better ideas, we will just listen.
Then there was a question here in the front.
Hello. Just for a community preparation, how can researchers lacking access to bistatic radar data currently simulate and test their retrieval algorithms for harmony?
So existing bistatic data is sparse, so I cannot give you a lot of it because we don't have a lot of it. So there have been some efforts to do campaigns, but an airborne bistatic campaign ends up being more difficult, I think, than a satellite bistatic mission in terms of organizing it and processing it. The tools that we are generating for simulating, they're in principle open source and they should be usable at some point, but they need to be at a state where you can use them. But the idea is that the tools can be used. And then if you want to know, contact me or contact people, then I will do it. But I cannot promise that they're usable today because they're being developed, so people release things when they're actually usable. But the tools will be, it's supposed to be an open science project, like all the Earth Explorers right now, so the tools should be available.
Very helpful, thank you.
There's one last question.
Yeah, so just a quick question about the DM coverage. So you showed it's 1 year, will be the DEM mapping phase to start with, and will you cover the global Earth with that, or is this on focus areas?
It will not, in principle, it will not cover entire Earth. The bottleneck is data volumes, so you cannot handle everything. It's also not set in stone, so I would personally push for at least one global acquisition just to have it, but it's not the plan. So there are some regions of interest, and we are targeting those, because we are targeting regions where we expect change. Okay, so it's not a global DEM is not a goal of the mission, but it would be nice to have, so you can keep asking.
Like a sort of harmony DEM as a new version sort of would be interesting, maybe.
I agree that I think having a reference, a harmony reference DEM would be useful for harmony itself. Yes.
Okay. Thank you, Paco. And with this, we go to the last presentation of the session given by Christian Rossi on the Earth Explorer 12 Hydroterra Plus candidate mission.
Thank you, Julia. You see lots of names here. There are actually many more. I started yesterday typing and I realized that there are more than 100 people working in this mission. So the names there are the mission advisory group of the mission, and the, let's say the core is a team in the bottom. Now, Hydroterra Plus, it's a candidate mission. So it's an Earth Explorer 12 candidate mission that is following a specific process. There are 4 missions that are competing in this phase. Hydroterra Plus, you will hear more about that. There is Cryorad, is looking into ice, the temperature profile of ice. That's a passive microwave mission. We have Keystone, looking at the atomic oxygen of the upper atmosphere. And we have ECHO, looking at the energy imbalance. Now, all these missions will be presented in a couple of weeks in Tallinn, in what we call user consultation meeting, where users and, let's say, delegates will be there to assess this mission, basically. And out of these 4, 2 missions will proceed into phase A. So now we are at the end of phase 0. I invite you in Tallinn, if you can, or joining online. So we just extended the deadline to Monday, the 22nd of June. So there will be a couple of days of presentations. And you can also follow we have a TV in ISA TV. You can also follow without registering, but without also asking questions. Okay, so this is general, but let's go into the mission. So we have a motto. The motto of Hydroterra Plus is revealing Harley water dynamics. And I want to focus word by word now. So water, that's the easy one. So what you see here, so this is the water cycle. I'm not explaining now the water cycle, but perhaps what I can mention is that Hydroterra Plus is looking at the terrestrial component of it. So it's looking into the atmosphere, into the cryosphere, into land, but not into ocean. Harley, so that's the key. So this mission is looking into sub-daily, up to Harley, you will see, timescales. And what is important here is actually finding and looking into the links, right? So there are many processes that are in the water cycle. And these processes, as I will show in a moment, they are on the sub-daily scales. And capturing this, it's really key, really, in understanding all of these processes. And dynamics, so those processes very often transform into events, into impacts. So you see some here, so mass movement, flash flooding, or irrigation, flooding in general. So the key here is really to understand this big picture with a mission like Hydroterra Plus. Now, why sub-daily? So if we look into these four domains and starting into the atmosphere, when we have like a severe event, so this is also called, or a severe event is MCS, mesoscale convective system. So if you look what is happening in the morning, then in the afternoon, and then in the evening, you actually see an evolution of the moisture into the atmosphere. We also call this integrated water vapor over the whole column. And actually understanding how this evolves really help us understanding the whole process itself. And another point is also understanding how can you then input this into, for example, numerical weather prediction, short-range numerical weather prediction, how we can improve this numerical weather prediction. Same for soil moisture. So when we look at moisture, this is varying as well during the day. So very often, if you just look at any irrigation cases in the figure, we have the soil wetting in the morning, then the crop uptake, the evapotranspiration in the afternoon, and then the redistribution in the night. So this is really important. So understanding this sub-daily cycle, let us understand the process behind it, this general hydrological response. In the cryosphere, this is also quite evident. So if you look what's happening again, morning till the evening, this is linked to the temperature, right? So we have a frozen surface that then gets an increase in wetness, release meltwater, and then refreeze in the night. Again, how can we capture this? And finally, the hazards. In this case, there is no morning, afternoon, and night. This can happen actually at any time. This is just to keep the story. But let's assume that in the morning there is also here some events. Then in the afternoon there is a slope failure, and then a post failure in the night. So. This is an hydrological driven hazards. So this gives you like the picture, no, on why a mission like Hydroterra Plus could exist. And if we look generally into these, so very often we use these plots. So where we in the x-axis we have the timescale, and in the y-axis we have like the coverage. We have all our events in there, and we can map the systems that are available at the moment. So in the figure on the right, in here, sorry, on the left, you see the microwave, some microwave system. And you see how Hydroterra Plus, perhaps I use the pointer. You see how Sentinel-1 covers like these events here, GNSS systems, they do cover this one here, but then there is a big gap in here, and this is what Hydroterra Plus aims to fill. This sort of plot you see often, so there is this paper that has been published recently by some of you, showing the same for solid Earth. So this again shows the need for it. Now we plan several level 2 products linked to these needs. So into the atmosphere, I already mentioned water vapor, with the various requirements. I'm not really reading this right now, it's going to take ages, but you can see the requirements in terms of spatial resolution, temporal resolution, and the uncertainty of water vapor, surface soil moisture. In the cryosphere, we would generate surface snow water equivalent and snow melt phase classification. And in the solid earth domain, hazard change maps and ground displacements. Now, how do we do that? Well, we are at Fringe, so not a surprise that we will use SAR. SAR is the solution to this problem, to the sub-daily water cycle. Why? Because, well, we look at any time of day, so that's a classic. And it's an interferometric mission, so we look this into this domain. We need large swath, so we are aiming to capture large swath from that position. It's a C-band radar that will work at HH polarization. Tomorrow, Andrea Montiguarnieri has a talk in the afternoon, in the morning, sorry, in the session, in the future SAR session, yeah, entering much more into the details of the system. Entering also here much more into the detail, but obviously there is a processing chain, right, to go to this level 2 products, which from GeoSAR perspective is something that we are not really familiar. There are some tweaks to the classics. There is a subaperture here processing in level 1, between level 1 to level 2. To compensate for atmospheric, let's say for the atmosphere. There are 2 branches here. So there is a backscatter branch and an interferometry branch. So soil moisture and snow melt phase will use the backscatter branch, all the other product interferometry. Now this is where things gets a bit more complicated. So we are at phase 0, we define this concept of operation. So this is a geostationary SAR. What it means is that it looks at a specific portion of Earth. So it's not like a LEO SAR looking globally. So, and this is the visibility area of the mission. This is a science mission, so what we want to do is to look into areas where we can study these processes on a sub-daily scale. And what we did is that we selected this region of interest where we can study these processes with this specific time. So the acquisition, the integration time is 1 hour. So, and if you look at 1, 2, 3, 4, and for example, you look at this region, you see this footprint, right? So what happens is that during the day, so this is 1 day, 24 hours, we acquire the footprint number 1, so this one here, every 6 hours. So 1, 1, 1, 1, and so on for all the other. So this is the standard mode of operation to capture this for at least 1 year into these regions, right? So this is our standard mode. and there are like in the middle four slots where we can task areas anywhere here. So for example, in Turkey or whatever. So this gives some flexibility. This is one mode, and then the other mode is like, okay, let's focus just here, and let's look this every hour. So what it means is that you don't have anymore 1, 2, 3, 4, but you have 1, 1, 1, 1. So you keep focusing here every hour. Let's assume that this taskable is also 1, 1. So what you have is that you have 20 times a day data over that specific footprint. We are talking of a large footprint. The size depends on where you are, but we are in the order of 300 kilometers. This is very powerful. So 20 times a day. And if we look at interferometry, for interferometry, you know, we need the same geometry, and the same geometry is guaranteed in couples that are like, like vertically. Okay, so this is the concept of operation at this phase. Now, within this, let's say this phase, we studied all these requirements, and we did many experiments to justify this concept of operation. We did experiments across all the domains. So these are also called OSSIS experiments. So we demonstrated how having data as Hydroterra Plus would improve forecasts. Compared with GNSS, would improve irrigation, would improve snow melt runoff sensitivity, would be able to see the various like melt, snow melt, let's say, phenomena. There is a lot here. Again, in Tallinn, we will really go into the details, but now I really don't have time to enter into this study in detail. Also, for Solid Earth, so what I showed before was for hydrological products. For Solid Earth, we had a look at some test cases over an Etna-like intrusion here to test the displacements, and a synthetic a lava flow change detection, but also some synthetic earthquake damage to justify these requirements, right? So this is quite important when you build a mission. You need to justify what you're doing. And this brings to this table, which is like a list of all the requirements. But what we do is that we need to demonstrate that this is feasible. So, and what you see in here in green, it's the result of this feasibility, right? So for example, for soil moisture, we have a target, a goal requirement of having 100 meters of resolution, but a threshold of 1 kilometer. What is feasible, 1 kilometer or 100 meters with this system? We check this, obviously, to generate this, and we demonstrated doing simulations and so on that the feasibility is for 1 kilometer for soil moisture, because at 100 meters we need a very small number of looks that doesn't fit with the whole system optimization, which is huge. So noise equivalent sigma 0, incidence angle, and so on. We also check, for example, where it works well, where it doesn't work. So we had simulations of this type of data, and for soil moisture, we can. Well, it's a classic. So when you have like high vegetation, is working with the degraded performance versus like short vegetation. So this has all been done for this scientific feasibility. We also ran a couple of campaigns to demonstrate this on the soil moisture side, Hydrodrone, and on the cryosphere side, HydroZui. So those are campaigns done with drone and Doppler radar, also looking at wind-induced decorrelation, and looking at in the cryosphere in general with this large integration time at sub-daily scale. The preliminary architecture, so we are in geo here, so there is a geospace segment with two satellite configuration. We are still in a phase where we have two consortia before coming into one. We have a lifetime of more than 4 years. That's the design, and a dedicated ground segment. And this is the flow between the level 2 requirements to the system requirements. It's quite complex, but gives you like a picture of the mission in terms of requirements. We also call this traceability. It's a flow down when you go from level 2 to system, or flow up when you do the performance analysis. I mean, the main point here is that the interferometric performance is driven by the interferometric products, and radiometric performance is driven by surface soil moisture. We studied all the possible error contribution, ionosphere, troposphere, RFIs, and so on. These are in the bottom here. Again, I think Andrea tomorrow will give a large picture of this. And in conclusion, well, first of all, I think a point is that what I just show now is actually available in the report for mission assessment, which has been published yesterday in Zenora, but also we have I actually suggest taking note of this one. So this is like a website that we have where we publish all the mission documents, mission requirement documents, report for mission assessments for all our mission, including HydroTerra Plus and all our candidates. Perhaps the last point that I can do is on socioeconomic. I didn't mention this at all, but this is quite important. So when you look at the sub-daily water cycle, you're looking at water security, you're looking at more efficient irrigation, you're looking at planning in general. You can link this to policy. So this type of mission would actually, fit and be quite, let's say, quite relevant from a socio-economic perspective. This was quick, maybe the first time that you heard about this mission. Again, in Tallinn, we will do much more, and I thank you for your attention.
Thank you, Christian. Are there questions from the audience? There's one here in the front.
Yes, a couple of questions. Well, first one. The areas that you have shown are already fixed?
At phase 0, yes.
Yes. Okay, so these are the areas that you plan to cover?
Yes, yeah.
Nothing on the ocean?
No, HydroTerra Plus is
completely out of the mission objectives.
Yes, it's blind over oceans.
It's a pity.
Yeah. But we did studies, actually, because that's important for the weather side on the impact of not having ocean into the estimates over land, and we found that it's limited. That was an outcome of the...
And the other question, if I can, is what is the retrieval principle for the snow water equivalent?
What is the?
Retrieval principle.
It's
for the snow water equivalent, interferometry.
It's interferometry, yes, yeah.
Then there's a question up there, or is it solved? No, okay. Then there's another question here.
I think you can go. There is one there.
Yeah.
Please.
Yeah. Could you elaborate on the rationale behind selecting HH polarization for the mission? But for the soil moisture retrieval, one would expect maybe VV or even the fully polarimetric data for a higher sensitivity. So I was curious why HH was selected for the mission.
This mission is not only soil moisture, so it covers like a broad spectrum of water products, and HH was the best compromise. So we actually ran also campaigns to demonstrate the suitability of this polarization, specifically for soil moisture, and it came out to be the best compromise for the mission. It's an outcome of this phase, actually, that HH was the best one.
There's a question here in the center. Dirk, put your hand up, otherwise they don't see you, please. Yeah. He's coming from upstairs. He's coming from back of you. Turn around.
Okay. Okay. So maybe I missed it. The frequency that you use is C-band, is it right?
It's C-band, yeah, that's right.
So have you looked into the potential radio frequency interference with Sentinel-1, for example?
Yeah, we run, absolutely. That was the key. We run a study. We use the 12 years of the database to look into this. And we put this into the requirements and into the modeling. It's not that big. So the outcome is...
No, it's more the other way around. What is your impact on Sentinel-1?
What is the effect?
The impact on Sentinel-1 acquisitions.
What do you mean?
Well, if you transmit, and you transmit also, or is it just...
if you look into the Sentinel-1,
yeah.
No, we did. No, we didn't. So we didn't yet.
Okay.
We look at the opposite. We do look at the impact of RFI. I think we will do if the mission is selected. Then we will start looking into the bigger picture.
Because I see that more as a challenge.
Yeah.
But okay.
So one last question to allow also time later for the discussion.
That was actually my question too, but additionally to that, is there maybe an opportunity for some opportunistic bistatic with Sentinel-1?
All brilliant ideas. I think we will look into all of these ones if the mission is selected. Yeah, I know about that. It's a potential, but we didn't study this yet.
Thank you, Christian, again. So with this, we are a bit over time, but now we still have some minutes left for the roundtable discussions, which, we would like to open up now. And maybe one question we thought about would be, I presented a lot on gap filling with ROSE-L and what we are not seeing yet, and also with improving with Sentinel-1 next generation. We have bistatic capabilities with Harmony. We are looking in companion concepts for ROSE-L. But which other gaps the community might see as a starting point at the moment? Are there any thoughts about it or comments in this direction? If not, we believe we are doing a perfect job at ESA and nobody has any open questions or gaps or other things to address. Now there's one.
Thank you. No gap analysis, but a question. There's a whole lot of data coming our way. What's ESA's policy on data retention and making data available? Sort of the long-term archive vision.
I mean, we follow the open and free data archive, such as for Sentinel-1, currently in place. Retention-wise, I should admit, I don't know, and also long-term archive, but it's definitely something, we have to keep in mind that also data volumes are growing, and indeed. But a very, very good point. There's another point there. Also, feel free, any other comments was just to start with a question to get the discussion started.
So I will follow up with the question I asked you earlier about the ionosphere for ROSE-L. So from the Japanese mission ALOS, ALOS 2, ALOS 4, from SAOCOM, from CONAE, and so on, and from NICER2, we know that the ionosphere is a big problem for L-band. So I was wondering why this mission, considering the experience from previous mission, is not considering having a separate band for correcting the ionosphere with a split, or instead of using the split spectrum technique, just a general question.
I'm not entirely sure if I got the detail of your question. But we are preparing for the uptake of the data. So we are having like this study running at the moment with DLR's Prime to look into the atmospheric effects and atmospheric mitigation. And we also will try to learn from the missions currently in orbit, so such as LOS-4, but NISA, I mean, that was shown yesterday. And we will definitely have the same problems. So we are trying to prepare ahead of time for the uptake by the community.
Okay, thank you.
Something that I can mention on that, it's a workshop that we will have in October. It's called For the Ionosphere, where we will try to mix the SAR community, so yourself and other working on the subject, with the community working on the modeling itself, so coming typically from the magnetic and other type of mission, just to make the community talk. So we will have this workshop, I think it's the 15th of October or 16th of October in Esrin. Registrations are open, so it's an opportunity to discuss ionosphere specifically in missions. Francesco?
Only to make it clear for the ionosphere, it's there's a side band. It's called like auxiliary band. I think this is planned. So I think it's for all subswaths of the Roselle interferometric wide swath. We have a subband. So there's no gap here.
Yeah, that was also like clarified after the presentation. Yes, thank you.
The question came up again.
Yes, yeah. And then there's a question up there.
Hi. Very less, I would say, technical question, more to the usage of the data. The good thing is that we are going to have tons of new missions starting from 2029, which means that we will have also some time for science to react, for industry to react, and then there are the Copernicus services that will benefit from those satellites. I think on your side it's really important that you give out early data samples, data format, for which we can prepare because all of this data will arrive essentially at the end of the next MFF, the next contribution agreement, and we will need to react to those then in the next one. Most likely, or at the end of it. So I was hearing of Roselle having 5 times the data volume, so we are constantly increasing on data volume. We will have missions like CHIME, hyperspectral, big data cubes, so it's something that I would say, please, let's say, give out early so that the science can be ready, industry can be ready, and we can then proceed.
Very good comment. Thank you, Lorenzo. I think that's very well noted, and we will work on this.
Thank you. Coming back to the problem of ionosphere in L-band, I think it's not only a problem, there can be solutions with C-band. You didn't mention how Roselle will fly to Sentinel-1. My last thing I know, a few minutes, but is this still true? Or?
No, that's what I showed in the slides. There are like 2 different options. Either that they fly in a convoy with a couple of minutes apart, Sentinel-1 and Roselle, or that we have a spacing in orbit of 3 days. So meaning like Sentinel-1, 3 days Roselle, 6 days Sentinel-1, and so forth. But that's a decision that will have to be taken soon. But for this, we will look into the different applications and the needs of the different applications, because it's a multi-mission and all the different applications have different needs. Yeah.
I think what we have seen from Zepka yesterday also on different deformation signals, it's not just a problem. Maybe it will just widen our view on what we see. We're limited so far on C-band that everything was fine and consistent. And obviously, as we widen the spectrum to other frequency, we may see different things. And so maybe this is a good argument to fly these systems close together so we can cross-compare and benefit from the 2 frequencies.
Yeah.
And reduce the variables. The ionosphere is pretty stable during this short time, obviously.
I think it's a very good point, but it's like, yeah, as I said, like the different applications requiring different needs. I know like for sea ice, they are also looking for like the convoy because the data are really complementary in sea and L band, but surface deformation is also very interested to have like the 3-day spacing for just to give an example. But I think for the ionosphere, I think it's a good point. Thanks.
Okay. I think if there are no further comments, recommendations, or questions, we have the coffee.
If you have anything else, you can also get in touch later in the coffee break, and we can still try to include it and discuss it. I think that's also good. Otherwise, I think there are no other last-minute comments. We thank all the speakers of the session, all the questions, all the contributions, and thank you.
Thank you.
Tiffany, and Bruno Miranda gave your name because you made a paper about VVH interferometry, explaining that it's not so nice just to add them up and there are some constraints there. In your paper, you say that VVH in SAR increases the density, but there are some constraints, some limits. It's not obvious. Space group as annual meetings, they represent ISA and the charter, which is a group of space agencies for disaster response. They invited us. You mean coherence or fringes? Phase. It's not the ground. The atmosphere. I worked on ISA project to implement a cloud environment for the core community of geoscience centers who are not experts in ISA. It's called the geohazard exploration. The GEP. And we have different chains. One is GEP snapping from Thessaloniki University. Another one is Amster from Liège Space Center. Different chains in a collaborative environment. And we were measuring the cost of processing, so you do full resolution, ascending, descending, $3,000 and so on. And then we started to think, okay, we do processing full res, PV and VH, so we increased 25% the density of this point. And then Nuno said to me, read the paper because it's not so obvious. I know what it is. You said the Vivian and the Yesh don't see the same thing.
Yeah. So if your doesn't have that
Is it a problem? Because one combination sees something, the other combination sees something else. If both say there is deformation, it's useful information. In my business on natural disaster, you know I work with USGS. You're American, huh? USGS are the members of the Charter Disaster Response. The hazard type for which we have the least maturity in terms of workflow for information flow is landscape. We have often charter activation in New Zealand. What is logging?
stop
integrate two AI-based models for inventory sites in the chart of I hope we work more with the US.
Yes.
Testing, yep, that works.
I don't know. Okay. Hello. So I'm Francesco De Zan. I'm here with Rowena Lohman to chair this session on INSA phase closure theory and applications. So welcome to the session. We have 20 minutes for presentation, and I've been told 2 minutes before we should stand up and signal that we should then transition to questions or to the next presentation. So we'll try to do this.
And yes, I'm pleased to introduce our very first speaker, Francesco De Zan. So I think the slides are up, and let you go.
Okay, so let's from here. This topic of closure phase, so I think I started it many years ago, and now it's there are many. I'm very happy that there are many presentations, let's see. So I'm talking about the inversion problem. So how we invert this signal that we find in interferometry, and how how I'm doing it now, which what I called, I'm tentatively calling it like multiple reference sun interferometry. Let's see. It's like the first time I'm introducing this concept. So going back, like, okay, closure phases are there. You have an example here on the right. This is on Namibia, Sentinel-1. It's 3 dates, and you have nice closures. And obviously, there are many different rain events which have happened over the same place in different dates. So how do you invert the problem? So how do we go back to a time series of soil moisture, for example? This is the typical problem that we are really, where I'm really doing something with closure phases. There are also other signals in the closure phases, but I wouldn't say I'm really able to invert the other signals. So when we first started doing inversions, like in the paper with Giorgio, we really started from closure phases and did like the standard inversion problem. We have these observations, and then we try to go back to the variables we want to see. And there are some drawbacks here, some difficulties, which have also been tackled in different ways by other people. But one thing is that the number of independent closure phases is growing quadratically with the number of acquisitions, so it's like not so nice. And also I would say there are some limitations in the modeling. So we have some models, but I wouldn't say they are perfect. So what I'm doing I'm trying to tackle this problem from a slightly different perspective, not the processing perspective, not the natural inversion perspective, but something that I learned at Stanford. They were talking about processing versus inversion. Professor Claerbout was talking about this. And so trying to process instead of inverting. So no inversion matrices, it's more like beamforming and stuff like this. And so the idea I'm trying to attach to is that closure phases imply the presence of different scattering contributions. And so my goal, my dream maybe, would be to identify those contributions directly and not, in the original signal, in the original scattering signal, and then doing the inversion starting from that. So this is the thing. This is the thing that I'm doing. It's a bit in the middle of the explanation, but I think this is maybe the easiest entry point. So what I'm doing, I'm taking two references, two reference images if you want, one here and one here, and I'm doing interferometry. So I'm interfering these two references with all the time series of star images that we have, like every image here for 1 to n. So I'm getting one series of interferograms on the top here, and one series of interferograms there on the bottom. So it's like 2 time series, and they're a little bit different. And then I'm doing the difference. Time by time, I'm taking the difference between the interferogram which is obtained with a reference A and the interferogram which is obtained from the reference B. And my claim is that this difference is typically very close to the soil moisture signal, or it's proportional to the soil moisture signal. So this is how I write it here, like there's some proportionality. There's one little thing I can say is that also this phase here, the difference down there is also a closure phase in a way, because it's a difference of 2 interferograms, and then there's a third interferogram which is not really explicitly there, but it would be the interferogram between the 2 references, and then you would have like really a closure phase with the 3. And the fact is that the interferon between the two references is the same for the entire time series, so it's just a constant. So actually, you could think this is also a series of closure phases. The process is rather elementary and fast. Once you have the two references, yeah, that's a problem. But once you have the two references, you just make two interferograms and you have immediately the difference and a value. So it's there's no big inversion, you know. And in my imagination, the two references could represent like two different layers in the soil, one a bit deeper and one a bit shallower. And so that the extra difference, the phase difference, is really the extra path traveled by the radar waves inside the soil. This is just my interpretation of some sort of mental image I have. The difficult thing is how to find the two references. And this is when it's a bit tricky. But in general, it's like I'm doing this with 3 acquisitions. I could also with 2, but in general, the trick is that I'm taking 3 acquisitions and I'm combining them in a special way, so that I produce a reference by combining them linearly. But there's also some sort of steering because I'm targeting 3 phase values. So I'm setting up the things such that the reference, which is synthesized by linear combination of the 3 acquisitions that I have, such that the reference will interfere with the original acquisitions and give these phases here, which I'm setting as an input. So I'm choosing which phases I want to see on these 3 images. Maybe it's going to be a bit clear. So I select a triplet of dates where I see a large closure phase, so that I know there's a soil moisture signal in there. And then I'm doing 2 things. I'm building like 3 little mini series of phases. One is just obtained from phase linking, just maybe the main component. And the second one is obtained by adding a little bit of a little delta to the first little time series. And the delta is built in a way that it should incorporate a soil moisture signal. And how I do this? Well, I do like a mini inversion on these 3 acquisitions. I try to understand which is the date which has the higher soil moisture value and the date which with the lowest. And so I do a little, like a mini inversion problem, but very simple on the also using coherence. But the idea is that I'm doing, then I'm forcing sort of this phase histories by building the reference in a way, in this certain way. And you can also see it, like if you interfere this reference with the original acquisitions here, which are here collected into this vector, you will see that you multiply like the complex conjugate of this vector on this side, and then you get like a covariance on the left, a covariance inverted here, and then basically what's left, it's only this vector here, xi, which is just like collecting the phases I want. So I'm generating twice, once for this time series and once for this one, and I'm generating 2 references, and then I'm going through the time series for the inversion. I actually could use just 2 references instead of 3. I have not done extensive experiments with this, but it seems to work. So maybe it's even a bit easier to understand, because with 3, maybe it's a bit more confusing. Once I do this, I see some limitations of my original model. Sometimes I'm inverting, and sometimes here in the gray, you will see all inversions, time series that I've done in a little area, like say 1 kilometer by 1 kilometer. I have maybe 8 or 10 time series, and some of them are flipped. The sign flipped. You see they're symmetric, and this is probably because the inversion on the original triplet was not correct. The model maybe was not correct. There's some sort of implicit assumptions that deeper layer have less backscatter, but sometimes it's opposite. So here's the chance for me to flip the wrong time series, to align them all together like I've done in here below, before averaging them. And here it looks like the signal to noise ratio, if you want, improves a bit. Since the problem is set in a processing perspective, there's a chance to go inside and do like these little corrections. And also you have access to coherence, of course, in all along the time series, so it's possible to to have an idea if of the quality date by date, to put maybe error bars. In a study for ESA, we inverted this over many sites, and in particular over Spain, over eastern Spain, we did it with 300 images, ascending and descending for 3 years, more or less. And here you see some results. Taken randomly, the results are very good in this case because the region is very dry, so there's not so much influence of vegetation. Here you see comparisons with ERA5. It's called here, my method is called INSAR here, and the ERA5 is the background line. And also we have correlation with SMAP, and also comparisons between RTI backscatter based from Vienna and this method. And you see, like on dry areas, the phase is very good, so we get typically higher correlations with SMAP than Sentinel-1 backscatter. But like in northern Italy, with more vegetation and agriculture, then it's the opposite. There's a similar concept that I've also tried to apply to phase estimation. The simple phase estimation is sort of phase linking to have also to avoid inversions and to do like continuous updates of phase-linked phases as time passes. And it's a progressive algorithm, so it's just adding or producing a new phase every time a new image is coming in. And it's a similar problem because also phase linking is a problem of solving closure phase problems. And how it's done in this case, it's just with one reference or one main reference. And this reference is done by combining linearly the past few acquisitions, or maybe with a autoregressive filter. So it's like combining infinite many acquisitions, but like in an automatic way with an exponential weighting, if you want, going back in the time. And this reference is then updated every time so that we can follow the coherence. But at the same time, there's a sort of filtering effect so that we are maybe improving on SNR or improving over decorrelating scatter. So we are forgetting things which are decorrelating, we are keeping things which are correlated for longer. So this reference is then interfere with a new coming SLC and produces a new phase. And the process is repeated. The reference is then incorporated, the weights are updated if you want. The new SLC is incorporated in the reference and is ready for the next SLC to come. This is very cheap. Okay. And of course, before this kind of, since it's a coherent filtering, before combining with real weights, we need to have rephased the SLCs so that they can be combined coherently. Yeah? So because otherwise you have troposphere on top, and any filtering will bring you zero in the long term. Actually, this thing was not enough to prevent like a drift, like the typical drift we've seen because of soil moisture or vegetation or effects like this. So in reality, I'm taking also some snapshots of this phase and keeping them and to make them to interfere with this reference as time passes. So I'm taking like maybe every year I'm taking a snapshot of this reference and keeping it as a phase reference to rephase this running or reference so that we don't drift in the long term. And this is sort of incorporating, making explicit many things which a typical phase linking algorithm is doing all implicitly inside. So, but you have access to this. This is the core of an algorithm. We are the core algorithm of a product of the analysis ready data product called now geocoded multi-look phases, of which you see here an example over Naples done with SAOCOM to simulate Roselle, because this is done in the context of Roselle, Sentinel-1, Copernicus missions. And you see here, for example, this product for 2 dates, which are just probably 16 days apart. And then these are multi-looked phases, so they're very small. They're already like 50-meter posting, so they're much smaller than the original images. And they're generated with this algorithm. And then here you see the difference of the two interferograms, which is also an interferogram, and you can reconstruct phases this way. Okay. it's difficult to, one problem is how to update these references over time in the case of the soil moisture thing, because I have, at this moment I have only one triplet, and then I derive from there 2 references, and I'm using these references for the entire time series. A problem is how to update this thing, and I was thinking I could sort of make a hybrid of the 2 algorithms, the one for the phase linking and the one for the closure phase, for the soil moisture inversion, so that we should also update this pair of references over time so that they don't become obsolete and we can still use them over time, because coherence will drop, and at some point we're not going to be able to invert this forever. And when I've tried to do separate chunks, like with overlap, separate, like 1.5 years with an overlap of 6 months, dividing the original time series then in 3 times and stitching them all together, you see there starts to be a bias, so probably vegetation induced. So we need this. And I don't know how do we best filter this vegetation. I have tried to apply the same algorithm also to hydrosoil data, campaign data for the Hydroterra Plus mission, and everything seems to be very reasonable. Actually, the sensitivity seems to be very, very high over bare soil. You see an example here for HH and VV. These are and the stations are here. Probably the discrepancy is probably due to the fact that the stations are not at the same depth of what we see, the few centimeters we see with the C-band. But when the vegetation increases, I still don't know what's the best approach. I really would like to be able to filter. I've tried a couple of weeks ago to do just coherent filtering, because here in hydrosoil we have a good phase reference, so we can just filter stuff in time. And this coherent filtering, like over the day, during day and night, it behaves differently, because in the day many more things are changing. So I was hoping we are rejecting noise, maybe vegetation-related noise, and this is happening. The coherence goes up compared to the original time series. This is the 2-day coherence, the original one, and after averaging the signals coherently before computing the coherence. But unfortunately, the improvement in the soil moisture inversion was not obvious, so it doesn't seem to be the best way of approaching the thing. But I'm still dreaming, how can we filter the signals? So I'm coming to the conclusions or summary. So I've shown how to combine coherently acquisitions to generate references. It's both for inverting closure phase problems, but also for generating simple multi-looked phases products from which would be equivalent to the phase linking. So this approach seems to work in 2 different things. Advantages are, of course, everything is rather fast. Steps are explicit, so one can intervene also inside. You can look at the coherence inside. You can look what's the model, if the model is doing interpreting correctly or not. There's some flexibility, as I've shown you, to correct like some mismodeling. But there are many open points. One thing is how to tackle temporal decorrelation when you have pair of references, how to update this pair of references over time, how to reduce the impact of vegetation. This simple low pass of 6 hours, of 12 hours doesn't seem to help. And also how to make weights adaptive to the actual coherence. One should probably try to tune in to the characteristics of coherence, like in a Kalman-like style. Perspective, I want just to say things that I believe in. So I think maybe it should be possible to identify even more than 2 mechanisms. Ideally, if we have 100 images, we should have even 100 mechanisms, so maybe we can identify even more than 2. And I think we have not exhausted the potential in interferometry to filter, focus different kind of targets, to follow the different phase histories, and maybe even for change detection once we have identified different populations of scatterers inside. Okay, thanks.
I think we have time for 1 question, perhaps? Yeah. Maybe 2. Yeah.
Thank you, Francesco. In your framework, you are making two phase histories, two reconstructed phase histories, which you are, assuming we are related to two different scattering behaviors. So in many distributed scatterers, we have likely more than two scattering contributions. And I was wondering how that would affect in the final results. In the conclusion slide, you mentioned that you are able to maybe estimate more than two maybe a scattering population in the reconstructed phase histories.
So I don't know if I understand the question. So there might be more than two, and this could affect, of course, the inversion. Yes, yes, it's true. Maybe in the case of vegetation, it's exactly what's happening. That there are more contributions, they're misbehaving somehow. If the several contributions are similar, like a narrow band, so to speak, maybe they just go together. But if they are really wildly differently behaving, then they destroy.
Okay. One more, and then we can have more in the discussion afterwards.
Hi, so I have a question regarding the temporal baseline that you used, especially that you mentioned that the difference between day and night. So if you are working with Sentinel-1 data, do you prefer using only one satellite? This way you know that it's passing on the same time, so you would have the 12 days interferograms to compute your closure phase. Did you try to look into if this temporal baseline, how it does affect the moisture index?
So I have not looked so much, but so for the inversion, for the final thing, we did even 3 years just with one reference. So the temporal baseline is the thing. But for the seeding triplet, maybe 6 days, 12 days, one should see some difference. When I try to apply the same algorithm to the hydro soil data, which have like every 10 minutes one acquisition, it was not working. I had to space the references so that I see something. So I cannot take 3 acquisitions one after the other, and there's no change. So one has to see some change to start the algorithm, to bootstrap the algorithm.
Okay, but using 6 days Sentinel-1 data, it didn't affect the fact that one is passing at night and the other one early morning?
No. I mean, no. They're passing the same. So all the ascending were processed together. So it was Sentinel-1A and B, and then every 6 days you have a time series, and then there's another time series at 6 hour difference in that case, but that was processed separately. And then the two could then incoherently merge somehow. I don't know how to say.
Okay, we should probably bring our next speaker up. Lorette Driek is going to be talking about subsidence in agricultural regions within SAR.
Hello everyone, my name is Lorette Driek. I'm a second-year PhD student working at IPGP and CEA in Paris under the supervision of Béatrice Pinel-Puségur and Manon Dalaison. And today I will present part of the work that I'm doing for my PhD with a presentation titled Tracking Subsidence in Agricultural Regions with INSAR, the issue of intermittent coherence and systematic closure phase. Now to go back to very basic things, as all of you INSAR users know, we are able to retrieve with INSAR a very precise time series of information over mostly stable scatterers such as buildings, rocks, roads, etc., and get a millimeter per year precision. However, whenever we introduce change in the in the pixel level, whether it is by adding vegetation of soil moisture variation, then we get a low coherence that gives us little to no interferometric information. Now, to better the coherence, we use the spatial averaging, also called multilooking, that allows noise reduction but with a downgraded resolution, and it introduces inconsistencies between the interferograms. Now, these inconsistencies can emerge from we can put them. We can see them, when we compute closure phase over a closed loop of interferograms. Here is represented a triplet. And what we get usually is that this closure phase is non-zero and has a non-zero mean. Now this is what I'm plotting here with, this has been computed with Sentinel-1 images over the region of Thessaloniki in northern Greece. And what we get here is that the mean closure phase is mostly positive, except in some regions, for example, over the city, it seems to be almost zero. So overall, it is mostly positive, which corresponds to a phase delay. And if we put it together with a land cover map from the Korean data set, we can see that systematically, whenever we have a positive mean closure phase, then it is where we have crops here in the yellowish colors. Now, this systematic phase delay over crops translates in time series analysis as a systematic negative velocity bias. So here we measure mostly over the crop a lot of subsidence, especially over at the region, over there. And we can start to discriminate between the crop types, but we will come back to this. And so this biased velocity is a problem when we want to measure ground deformation of the order of the same order of magnitude. So the closure phase is linked to different processes and variation in the backscattering properties of the pixels, and this has been linked by Duza and collaborators to different processes. The one interaction with interaction of radar wave with a variable dielectric, or interaction of the radar wave with a volume. And it has been linked, as it has been presented, to soil moisture, but it also has been linked to the land cover. So this is a graph from Maxudi and collaborators, where we see that the closure phase accumulates more over cropland. There's also been studies about its relation to precipitation. So there are a lot of physical reasons for this closure phase, but we can also, it also depends on some processing parameters. For reference, this is a figure from Ansari and collaborators that shows that it depends on the temporal baseline, for example, and that the shortest the baseline, then the further away from zero the mean of the closure phase will be. Now, if we want to, so we've said that there is a systematic phase delay over crops, and now if we want to look at the crops, then we have the contribution of all of these variables and even more. So it is a multifactorial environment, which makes it challenging, but as it is human managed, it is also partially predictable, so it makes it a good laboratory for closure phase studies. And we've chosen the Thessaloniki region for this study because of different things. First of all, it is a very diverse agricultural region in a Mediterranean climate, which means that we have some good coherence in some months of the year. But most of these crops are very water intensive, which calls for a lot of irrigation. And this irrigation has been linked to subsidence in the region. So this is what we see here on the EGMS map of velocity here. And we see that we have some subsidence identified in the region here, which is what we showed to be crops before. But these studies have limited spatial coverage. And so what we are wondering about with this region is how we can, first of all, characterize the phase delay over these crops in the region. And then the main goal of the PhD, and in general, I would say, is can we extend the deformation estimates for subsidence monitoring? So I will first present the spatial temporal characterization of the closure phase on crops over multiple years in the Thessaloniki region. And then I will speak about the perspectives and the motivation we have to go from phase error to velocity bias. Now, our processing setup is as follows. So we're using 5 years of Sentinel-1 A and B interferograms with building short baseline interferograms, so 6 and 12 days. And we use a large multi-looking window to ensure unwrapping and then inversion for time series analysis. And we'll build the corresponding triplets, so the 6, 6, 12 triplets, and we also will use the coherence, which is shown here, which is the weighted correlation between the pixels within the multi-looking window. The indicators and the variables we're looking at, here is the land cover map that I showed before, but we will only focus on 3 types of crops. So non-irrigated in green, permanently irrigated in blue, and the fruit trees in purple. And we will use the urban fabric as a reference. Now here is the mean closure phase that I showed before. And as I said, you can already discriminate between the different land covers by looking at the mean closure phase. Then in addition to the land cover, we'll use the NDVI. This NDVI has been computed using Sentinel-2 super resolution images by Sylvain Ferrand of Duza Bio. And he computed with interpolation a time series for September 2020 to September 2021. And this is an image of the NDVI in July of 2021. And again, we see very similar patterns between the land cover and the NDVI. Finally, we will also use the coherence. So what we can get, and we will in the end speak about the vertical velocity. So what we can see from these maps is that we have very similar pattern, but we cannot really identify the correlation between them. Some are moving in one way, some moving in the other way, depending on the land cover. So this is what is represented here. And now we will wonder, what about the temporal correlation between them? So here, we to study the temporal relation and the temporal evolution of the closure phase, we plot here the cumulative phase closure for the triplets that we computed. And what we get is first, if we compare a non-irrigated arable land and the permanently irrigated here, we can see that there is more error accumulated, more phase delay accumulated on irrigated crops than on non-irrigated crops, but this seems to be mostly a continuous accumulation with small seasonal variation. However, on the fruit trees, we can see that even though it accumulates way more phase delay over time, we can see that this accumulation is mostly seasonal, so we have a very high acceleration in the summer and then a plateau in the winter. Now, if we want to look more into the seasonal signal of this, we detrend this cumulative closure phase, and we plot it, together with the coherence. So here in the darkest color is the coherence, and then it's the cumulative closure phase detrended. And what we get from this figure is that we have a mild anti-correlation between the two, with mostly a delay between the peaks. So when the coherence drop, the phase delay does not start to accumulate right away, and it starts accumulating after a few satellite passes. And if we look at the other land covers, then we see that we have a very similar variation in the coherence, but that do not account for the very high seasonal variation between the different cumulative closure phase. And so we have, as expected from the trended series, a very high seasonal signal for the fruit trees. So this is here, and yes, and we see also that we have year-to-year variations that, again, are not accounted for entirely with the coherence. Now, if we want to look at the coherence a little bit more in detail, we plot here the mean coherence for the 5 years of the study, so the mean annual coherence. And what we get is that we have some difference between irrigated and non-irrigated, with very similar variations from November to May, and then it starts diverging. Now, if you want to compare to a rough crop cycle for the main crops, the predominant crops for each class, we see that globally there is some correlation, and we see, especially for the growth phase, we see that the coherence drops for the irrigated arable land in the summer corresponds to the growth phase for the cotton. And we attribute this so to the continuation of the crop growth and more irrigation during these months. And finally, so if we don't have more detail for now on crop cycles or precise crop distribution, so we use the NDVI as a proxy for the crop growth. And here we plotted together with the cumulative closure phase, the trend that we saw before, but for the corresponding period, so September 2020 to September 2021. And what we can see is that we have a high correlation for permanently irrigated and fruit trees, but with a correlation coefficient of 0.7 for the fruit trees, but we do not see that for the non-irrigated arable land. So the NDVI, the closure phase probably captures a lot of things that we can see in the NDVI, but it is, again, not sufficient to explain it entirely, at least the seasonal variation. So to conclude this part on the spatial temporal study of the closure phase over this region, we see that we have some correlation, sometimes pretty high, between all of the observables that we have. And so the closure phase does encapsulate a lot of crop-specific characteristic and physical characteristics. But again, one is not able to completely encapsulate everything. Now, to come back to the bias that we're speaking about at the beginning, and if we want to measure the subsidence in this region and get rid of this bias, then we are trying here to characterize it. I mean, we would like to characterize it using the closure phase characteristic and the physical cause of the closure phase. But there are also mitigation methods that already exist for to get rid or at least mitigate this bias. So we can mask the bias pixels, or we can use long baseline stability. The problem is that sometimes we do not have long-term coherence, so it also adds other problems to the mix. And we can also weight the spatial averaging depending on the type of crops that we find in the pixel. But since we are able to characterize the closure phase physically, at least partially for now, maybe we can also use this characterization to tell us something about the velocity bias. And so maybe we could one day predict and correct the bias based on its physical understanding. So now to motivate a little bit this, here is the time series that I showed before, I mean the velocity map that I showed before. And this velocity map has been computing using only 6 and 12-day interferograms. So as these are the most susceptible to phase delay, obviously we expect that if we add longer baseline to the mix, then it will mitigate this bias, and this is what we see. And if you focus mostly on this region here, then we can see that. So if we add 18 and 24-day interferograms into the time series, we already have a pretty big difference in the velocity estimates. And now if we add even more baselines, 1, 2, 3, 6 months, and 1 year, then we can see that the velocity, the subsidence that we measured over the fruit trees is almost entirely gone now, but we still have some subsidence measured. So we think that even though we add more baselines and we increase the computational cost, then we still have some residual signal that might look like bias. So to compare it and to have a kind of a reference point to start trying to estimate this bias, which is difficult because obviously we do not have ground truth. We can compare it Oh, yeah, sorry. So what we can see from this is that the bias has a crop-specific component, as the phase delay had. And it also, yeah, it is reminiscent after minimizing. Now, if we compare it to more stable time series, here we have a velocity map computed with PSI by Michael Fumelis of the Aristoteles University. And what we can see is that we do measure some subsidence with the PSI, as we did on the EGMS velocity map. But when we compare it to our time series, then we have some zones where the residual is 0, so we do measure the same. But then in all of this region, I mean, I don't know if overestimate, but we estimate more subsidence with SBAS. So it is also very difficult to compare two different these types of two different methods. But to conclude and to motivate again why we want to extend the coverage of the measurement, here is our velocity map, where we removed the pixels where we found a PS measurement, and we can see that although probably some of this information will be difficult to debias, there should be some very interesting interferometric information to retrieve from this. So now these are the conclusions. So we have a positive trend and a seasonal acceleration in the cumulative closure phase that is crop dependent and agrees with the local crop cycle. So the closure phase is a quantity that does give information about the plant growth, as I'm sure it will be presented also after. And that translates other things that the coherence does. And we expect that this cumulative error will translate as a velocity bias with the seasonal component, making it even more difficult to retrieve in the velocity. But maybe we could, using the physical meaning behind this phase delay, help extending the coverage to agricultural areas. Thank you.
I think we have time for a question. One in the back.
For each multi-looked pixel, how do you consider it, or how do you determine what surface type it is? Does it have to contain like over 50% of that surface type, or 100%, or like do you use a threshold?
Yeah, so there is obviously a lot of mixing since the very big pixels, but we use the most dominant class inside the pixel, or the mean in general. But I guess, yeah, it will depend, the estimate will depend, and probably if we look more into crop types, we will have to decide which crop type has more influence, even though it is less present into the pixel.
Okay. Thank you.
Okay. Thanks, Laurette. I think the next. Oh, you want the last question? Okay.
About your cross-validation and ground truth integration. To untangle the fading signal bias from actual deformation, you corrected the time series, right, with the EGMS and ground leveling or GNSS data. So why is independent validation particularly critical when adjusting network connectivities to filter out phase inconsistencies?
I'm not sure I really understand the whole of the question, but we didn't correct the time series. We just compare it, and there are very few GNSS stations on ground, so it's very difficult.
Just for ground validation, right?
Yeah.
Okay, thank you.
Yeah, sorry.
Okay, I think we need to, thank you. I think we need to go to the next. Next presenter is Irena Heinzek from ETH Zurich and DLR. And she's going to talk about biomass and soil moisture retrieval.
Okay, great. Yeah, thanks for this introduction. Yeah, we are switching a little bit towards, let me say, exploration of longer wavelengths and perimetry. So I would like to add here a little bit on this discussion perimetry in order to see how we can resolve all these problems that we have with vegetation. Perimetry would be one thing in order to understand and characterize what kind of scattering processes do we have. So therefore, biomass is a great mission to be explored, and this is what I would like to do here. Probably I can skip this slide now already because I had two previous, or at least the last speaker was very clearly saying what the problem is when we have vegetation, so that's very great. So the vegetation becomes important when we have high spatial resolution data, SAR data, right? That's much more important. Nowadays we have SMOP and SMOS, which are not accounting or model-based. They have smaller accountments in terms of vegetation rejections or cancellations, but if you have very, very high spatial resolution, which is less than a kilometer resolution, then vegetation becomes a difficult task to be avoided. This is clear for higher frequencies too, are stronger affected than lower frequencies. I mean, that's clear, and vegetation and soil moisture changes, so the vegetation changes in terms of moisture content of the vegetation as well as the moisture itself on the soil are very, very difficult to detangle. And we know that most of our surfaces, land surfaces, are really covered by either by vegetation itself or are agricultural managed. In the last decades, I would even say there have been a lot of approaches in order to try how to detangle vegetation, or let me say volume scattering or vegetation scattering from surface scattering. One of these was using decomposition techniques. This is purely using polarimetry. Which can be done in different ways, where you try to use very simple canonical models in order to separate the different scattering contributions, like, for example, surface scattering, dihedral scattering, and volume scattering. Or nowadays, we also try to use now a model-based tensor decomposition in order to detangle this part. What we have also tried to do is to use Paul-Inser, so baseline variations, in order to separate volume from ground. And for sure, you can also use multiple baseline acquisitions, like, for example, tomography, where you try to get the volume separated from the ground contribution. However, we were also trying to look more and more a little bit into this framework, what the INSA can do, because most of the missions today that we have are zero baseline missions, and therefore also here it would be great to have a look on it. Francesco was already saying, so one of these, or has introduced very well, the closure phase. We have started also to work on this using a model-based approach with Zwieback et al. And separately, we have also looked what is the influence of the vegetation moisture actually with the de-interface. And this has been done also and published by Brancato. But however, these have been two different sensitivity studies. And if you like to know a little bit more how we can combine also these two studies, then it will be the next presentation which we'll be focusing on. I'm not focusing on these, but I'm just focusing today on using longer wavelengths and using polarimetry in order to see how we can characterize the scattering processes. What we know today is C and L band is clear. L band has stronger penetration into dry soil than C band, this we know. We have longer wavelengths, less sensitive to vegetation. This is also what we always assume. But still it has, as we have seen it also now, it has a sensitivity to vegetation moisture content. And L band has a smaller de-interface variation over bar surfaces than, for example, C band. What you would like to know is, does P band have stronger penetration into dry soil? Potentially, yes. We always assume this. Are we sensitive to vegetation on top of the soil? Because we have longer wavelengths. Is vegetation still a big issue here if you use P band? And how strong is the de-interface variation, because this provides you a sensitivity on how good can you estimate soil moisture later on. Okay, let us go on what we started to investigate. So we were in principle looking to one model, which is providing in principle or modeling the coherence. This has been a model developed by Zwieback et al., where you're predicting in principle the interferometric coherence. With, in principle, two main components. We have the subsurface volume component, and we have the surface term component, and in front, this volume to ratio, which is important. And for these contributions, we have added also a small perturbation model, where we have the sensitivities adjusted to HH and VV polarization. This has been, let me say, go back, because that's a video. Just trying out if it's launching. Yeah. No, now it's not anymore. It doesn't matter. No, it's okay. So what you would see is in principle now it's starting. It's a variation of the HH interferometric phase, right, which has been inverted into soil moisture, and that's soil moisture maps for different time steps, mainly over bar surfaces. This has been done on an airborne experiment from a UAV star in Canada. However, we start with this model in order to investigate what is the sensitivity now on longer wavelengths. This has been shown on L-band. Let us have a look what we see in L-band. What you see here are two main plots, the one for the coherence. So you see here moisture against the moisture change. So if you change a moisture content of around 10%, then you see we have a change in the interferometric coherence, which is around 0.5. If you have a moisture against the change of the moisture of 10% change between 10% and 20, then you see you have a change here of the interferometric phase of around 60 degrees. If you go now to P-band, we see this is strongly reduced, so we have a higher coherence in terms of change and also a lower phase variation, right? So that's important to remember when we're now going from L-band to P-band. So in principle, the main model observation shows that coherence of P-band over surface is significantly higher than L-band, so the coherence is higher. The phase variation is smaller in P-band than in L-band for the same moisture content, and P-band is more sensitive to stronger soil moisture changes than L-band, because if you go here to stronger soil moisture changes, right, then you keep kind of the same phase, whereas here you have still some sensitivity in terms of changes. So this means the sensitivity is higher in terms of higher changes in terms of soil moisture. Let us look a little bit now into the data. We have chosen here one data set over Argentina. Why we have done this? Because biomass is in principle a non-zero, let me say, mission, which provides also spatial baseline. And we have tried now to use zero baseline acquisitions, which has been only acquired, some of them over certain areas here over Argentina, where we had a 3-day repeat. You see all the dates are here in June from the 7th to the 25th, so with a 3-day repeat. And we see also on the capacita versus the date plot very well that it's very, very close to zero baseline acquisitions. Over this area, we see already we have one region which has very strong agricultural fields, and these one part is in mountainous areas and has also some forested parts. Okay, if you look now to polarimetry, because this was what I said would be interesting to see, what do we see in polarimetry? We have plotted some of the main polarimetric observables that you have here, the Pauli RGBs, the Pauli SHV, the entropy, the polarimetric entropy, anisotropic alpha, and you see already some differences over, in principle, the different regions that we see here. Mainly we are interested in this agricultural fields, therefore I will do now a zoom in order to see what can we see. Okay, we have here now P-band Pauli RGB, so this is the combination where we have HH plus VV, HH minus VV, and twice HV. And what is interesting, we see differences, right? We see differences not really particular in time so much, but what we see, probably we need to zoom in even closer to see really particular differences. But what we can already distinguish are regions, right? We can distinguish regions which are darker, which means here we have probably less vegetation ongoing, but they have still some, and you see it here, quite reddish areas, so which means we have quite a strong of dihedral scatterer. But we have also regions which are high, have in principle high signals. Well, these are the areas which are in principle stronger vegetated. Let us go to the anisotropy. What does it tell us? The anisotropy is in principle extracted from a coherency matrix and is the second and third eigenvalue after diagonalization, which means what we see here is in principle the secondary scattering mechanism. And again, what is interesting here, if you focus on one of these regions that I was showing, so we have some stronger or higher anisotropy over some of these areas. And if you, in other areas, and these was the high vegetated areas here, are very, in principle, are lower. So the anisotropy, you see it already, is a little bit noisy affected parameter, but it provides you secondary scattering mechanism, which means there's some scattering ongoing for sure in this area. So this means, again, if you interpret this, that we have some vegetation on top. When we look now to these two fields here, focusing on these two fields, and we see that some changes appear over the second field here, and it's slowly disappearing here. It's very, very well seen, which means we have some practice ongoing over this specific area. And you see also, we see it very, very well in the anisotropy. When you go now to the alpha angle, which provides us information about which kind of type of scattering mechanism do we have, then we see we have a quite bluish but also greenish area, which again, we see we have some vegetation there, but mainly it's an area already where we don't have so much strong vegetation ongoing. Again, if you look focusing on this region, we see some smaller changes, but they are not so apparent over the second image or the second field that we have seen just before in an anisotropy. If we go now to the HH-VV coherence, which means the difference between HH and VV, also here we see that we have a difference. So we have we have a coherence which is lower, and lower means we have a strong difference between HH and VV over certain areas. And again, here we see very well over this region, which we assume is vegetated, it has a strong decorrelation. And then we see also decorrelation ongoing in time over this smaller second field that you see here. When you look now to the phase, so also within the phase we see some differences, right? It's also something that we see, and what is very interesting, again, appealing, is this one field that we saw before, and also, again, the three fields that are popping here up. So this means really the parametric phase is providing us also some indication of that vegetation is appearing here. Otherwise, you see it's quite greenish, which means we have quite a lot of flat surfaces, which means also HH and VV are quite similar to each other. If we go now to the cross-polarization and do a coherence here, then we see already we have areas which are lower, so have stronger decorrelation. This is really also over a region where we have low signal, and again, this is actually the same signal as we have seen before, right? Here we have very low signal, that's clear, and over this area, which is very bright, we had, in principle, stronger vegetation, which means we have a stronger correlation between HV and VH. Okay, this has been the parametric observation. How do now the interferometric coherence looks like? So let us go now to interferometry and to have a look on the different polarization parts. So this is now the interferometric coherence and VV polarization. And again, if you look over the same areas, or in general over these areas in time, so here we see a difference in 3 days, 6 days, 9 days, 12 and 15 days, and we see already the interferometric coherence is a little bit in general going down, but what is also interesting, for several fields we have different decorrelation patterns here, depending on the vegetation on top of these fields. If we go, and what we also see that's also interesting is in principle the decorrelation because of the management of the second field that we have seen here before already in the parametry beforehand. If you go now to HH, we see HH in general tend to be a little bit lower in terms of coherence. So VV is much higher, HH is a little bit lower, which is interesting, right? And if you go, so that's in general, and if you go to HV, it's even lower, right? So this is clear because we have certain effects. We have, for example, low signal first, which could be an SNR effect, but also we have some other changes. Okay, what are now the triplets look like? So the triplets are made in the 3 days. So we have generated in principle 3 pairs out of our 6 acquisitions. So we started with the slowest distance, so these are the adjacent distances only now here in VV. And what is interesting, you see some patterns. So you see here some bluish patterns, which means, so I have in principle a negative phase, but then you see slowly with the second set of triplets, this is fading out a little bit, becoming more reddish, here also becoming more reddish. So this means we have in principle a kind of a change in the observation, even though the time span is not very long. Remember, we have only 15 days between the largest time span. But also you see here, these are changes becoming more positive here. So we have some differences ongoing within these regions. Okay, and again, we see also the differences here of the field. Do you remember this one was the stable field, and this one was a field which we were seeing that some practice or some changes are ongoing already in the anisotropy. If you go now to HH, everything is again, as said, a little bit lower, but then means also the variation of the phase is a little bit stronger. So this is what we can see here. So in VV we have the variation of the phase is smaller, and the variation in principle in HH is a little bit larger. So this is what we can see. Therefore, it's also a little bit more pronounced in principle the bluish part, but then it's fading out with time. And HV, you see it here, the problem is with HV because we have very strong decorrelation, we have very, very strong also variations here, therefore if you scale it on the same scale as HH and VV, then you see it like this. If you would scale it a little bit smaller, then you would probably see a bigger variation. But still, we see what is still interesting, we still see the differences in these fields here due to the practice. So you have also still some signal. It's not only noise, but we have still some signal that we can observe. Okay, let us a little bit summarize in terms of the phase triplets. What we have done is we just zoomed in one of these fields, which we have the yellow dot in the middle of the RGB image. And you see with the HH triplets, the error, so the standard deviation bars are much wider than, for example, VV. This is a little bit what I was saying before. We have a little bit higher coherence in VV, therefore the phase is much more stable, and in HH we have a stronger variation, therefore also the standard deviations is higher. And the same is also in principle for HV and VH, which are the in principle the difference. What is interesting, you see in general, we have the trend to become, let me say, to become closer to zero. So we are starting somehow by 20 degrees, or in principle VV is then by 10 degrees. So this is in principle the variation of the p-band. This is a little bit what we expected already from the model. The model was saying that the variation in principle of the phase is not so high as, for example, in L-band. So the variation in terms of phase is smaller. So this means also a better phase calibration is very needed if you look really for p-band. Okay, let us go to the inversion. We just used the Zwieback model. As Francesco was saying, there are also there are also other models available, so that's just an example. This is now the inversion for all of these dates. If you zoom in again here, this is the soil moisture over a certain region, and again, we see some differences over these two areas of interest here. Let us have a look a bit. So we have a very first preliminary analysis of it, again, over the same dot, which is the yellow dot. We see, in principle, the variation. Take care, don't look in the first value, which is 10, is in principle the inverted soil moisture of 10%. It is an initial value, and then slowly it's in principle adjusting to a certain area. So what for us is most important is to look not for the absolute value, but look for the differences, right? The difference between the first, the second, third, and fourth, and fifth. In principle, the difference here is 2 to 3 volumetric percent, and that's quite valuable when you look in principle to the soil moisture estimation using now the SAUCOM data, because these are regions which are also acquired by SAUCOM L-band data, and they have a very pronounced soil moisture investigation. However, it's very, very rough because it's done over a huge area. You see the polygons here, and we have very, very small fields. But the variation here is around 1 volumetric percent. However, I would not really go for certain for it, but just to say it's in the same range and don't look for really absolute values. Okay, just coming to conclude. So what we have seen using p-band now, we have high intercoherences observed over agricultural fields, which is good. So it's not everything noise, which we could imagine potentially, but it's not. Coherences are varying with polarization. That's also very important to see. The phase triples show variation over time, which is interesting, even though we have only 15 days. And these variations are polarization dependent. And if you look to the inversion into soil, shows slight variation over time, which is in the range of 2 to 3 volumetric %. However, coming back to my initial question, does P-band have stronger penetration into soil? Yeah, it's still an open question. We don't know, right? So, and these fields have been in June mainly have been not so strongly, and this is what we see with the porometry. Mainly surface scattered areas, so there are not so much vegetation on top. Are we sensitive to vegetation on top of the soil? Yes, we are, and this is what we have seen. Let me see with the polarization, but how much, it's still not clear how much vegetation is on top of these fields and how we can really, or how potentially this is really influencing in principle our signal. And how strong is the interface variation? We have seen it's small, it's kind of what we would expect, and probably we need a longer time series really to have more answers to these questions as we have them now with only this 15 days. This means in principle, first observation have been made, but further investigation needs to be done. Yeah, thank you for your attention.
We think we should move on to the next presentation, and I also want to so thank you, and we will have also a session for discussion, so if you have questions, keep them. So we move to Henry Schauer, also from DLR, German Aerospace Center. How late are we? 5 minutes, okay. Not too bad.
Yes, first of all, thanks for the opportunity to present here, and thanks to my co-authors, Nikita, Simon, and Irena. I will be talking about differential solar interferometry, as we've seen in the other talks, but very much on an inversion-focused perspective and focusing on soil moisture retrieval over vegetated agricultural fields. I'll look, that's the second point, into the empirics a little bit. How does vegetation impact the interferometric phase in our data set? And then move on, the third point, bare soil models, how do they perform over vegetated soils? And then try to advance this in some way, more or less successful, I would say, to account for vertically oriented vegetation with a simple cylinder representation. That's our setup. We use DINSA to minimize these geometric effects using repeat bar zero baseline configurations. We move along azimuth and look into line of sight onto our scene. And for example, then there's a change in soil moisture, and there we actually then see an increase in range, an increase in the phase, and this is how we can invert our soil moisture. But there's also vegetation on the scene and surface roughness, for example, so most of the time a lot going on. But actually both models that are represented here, and I think that's the only two models that are on the market, that's the model from Francesco and that's the model from Simon Seebach, and they are both assuming that there's no vegetation, right? And Francesco, please correct me if I get your model completely wrong, but the model, I call it the Dijon model now, it assumes a flat interface in an infinite volume, and this is in contrast to the model from Simon Seebach, which is a bit more complex, and it introduces two parameters. That's the volume to surface ratio F, so adjusting for a surface term and a volume contribution. And then inside the volume, there's the parameter that's A1, that's the soil profile, meaning dielectric contributions coming more from the bottom, the middle, or the top of the soil. So that's the setup. I will be focusing on the model from Simon Seebach in this presentation. Data I use is from the AgriRosL airborne campaign. So I focus on L-band, that's what's represented here in Pauli RGBs, and it was planned to cover basically the entire vegetation period. We are seeing more blue colors, more surface scattering. Here in April, that's the topmost figure. In the middle, in June, and then in July, we're getting more vegetation, more dihedral and volume in green and red colors. And in my case, here in L-band, it's 60 centimeter by 130 centimeter resolution, and normally a 6-day temporal baseline to simulate then the ROSE-L mission. And I won't go into further detail because there's a whole talk also from Irena in the session Future SAR Missions and Concepts to Tomorrow. Right, so that's the data I use, 23 acquisitions. For me, the main interest starts in the middle of May, 21st of May roughly, when the maize and the potato fields start to be vegetated. Before they were bare soil. That was the talk last week at Aula, where I focused on bare soil performance. And here now, starting with vegetation in the middle of May, the wheat field was already vegetated in April. But that's just to have some ground truth, some reference. We measured every 50 meters the soil moisture, and additionally recorded the plant height. There is additional data from LMU in Munich. They covered a different site with also extensive vegetation measurements, but this data is not available yet, and therefore proper forward model development and also validation was not exactly possible. Just to hint at these in situ data limitations, the soil conditions were very much heterogeneous, so this 50-meter distance is not really capturing everything that's going on. Additionally, I did some cryogenic interpolation because our points were not as precise as we needed it, and therefore it is introducing some additional uncertainty. Also, the integration depth is a bit mismatched between L-band and our small in situ sensors with these 10-centimeter metal rods. Right, then let's jump into the empirics. How does vegetation impact interferometric phase? And we've seen from the talks before, that's also what literature tells us, that it's quite complex. Vegetation causes normally a positive phase shift. This is what we observe, but it can also be negative. Importantly, it's very much polarization dependent, but then again, it depends on what vegetation structure and type we are looking at. Generally, the main assumption that is made is that the phase similarity depends on the anisotropy of the medium, but then there's additional factors like the polarimetric diversity in the scattering phase. I'm just reading this because it's quite detailed. Dichronism, that's like birefringence in the amplitude. Differential movement of dominant scatterers can happen. There's noise-like decorrelation. Also multiple scattering. We are normally using first-order models. This mulching scattering in the volume. Also dihedral scattering, they are not regarded normally. For bare soil, we expect there to be differences in polarization depending on the field. That's a thing from the Dejan model that it starts or assumes that HH and VV are the same. And with the Zwieback model, we can differentiate between HH and VV polarization, which should give us a bit of a performance increase. But again, depending on the field we're looking at. Vegetation overall is potentially influencing our phase a lot with up to 90 degrees for certain crops. It's very much birefringent crops, so up to at the 6th day baseline up to 90 degrees for wheat, for example. I use the phase triplets more as a means of preparing them for satellite missions, but as I'm using airborne data, ionospheric influence and displacements are also not happening that much in our region. Sorry, that's back. Yeah. So looking at the data, I will guide you through this a little bit. We've got our interferograms in the top row, our coherences, and then we can see our images and how the vegetation is developing. And the first thing, I think that's quite obvious here with a height change of 40 centimeters for those 2 dates. We're also seeing a positive interferometric phase, even though the soil moisture change for that date is negative, so we would expect a negative phase, but this seems to be compensated by this 40 centimeter height increase. That's the maize field on top here. For other dates, it's a bit less clear. The height change is a bit smaller. We're also seeing sometimes negative phase in some crops. So here I think that's an hypothesis, could also be some drying that happened in the crops. Looking at soil moisture, it makes sense to not look at this part so much, but more at this part. And here, surprisingly, that's a bit, was a bit of a surprise here in the sense that we have an increase in soil moisture of 7%, but the phase is actually negative, which I didn't expect. Could be because it's not only phase velocity, but also the penetration depth, and also the plants were still dry. It was a very rainy day, that due to the penetration depth, we have this decrease in range. For bare soil, or more bare soil conditions, also the dates before, it's good that we see that we actually get a positive phase with a positive moisture increase. And the coherence, I mean, it differs a lot. In these upper fields, it's a bit higher. In these lower fields, lower. In these lower fields, it tends to be a bit higher. We can also look at just 2 different polarizations, HH and VV. HV and VH maybe are not that interesting right now. And we can see that they differ between polarizations, but also between dates. So these coherence regions, they wander about quite a lot. So that's not, I mean, I think there's been quite some studies looking at only polarimetry, and this is now polarimetry and interferometry. And again here, this movement is also apparent. Right, so let's come to the model inversion. Here we are doing time series optimization. We also, similar to how it was done in the last talk, we fix one value and then optimize the other n-1 moisture values. I'm including triplets and coherence in the optimization. The loss function is explained in more detail here. We're using an optimizer, ADAM optimizer with 180 iterations and applying 100 looks to both coherence and triplets. The model inversion is applied to all dates, and then we validate using the 3 sampled reference fields. There's more to the inversion process. You can adapt learning rates, for example. You have to clamp the data and so on and so forth. Most importantly, I masked out coherence below 0.35 before the inversion just to get a bit more stable results. And then, before jumping into the vegetation or the combined model, I think it makes sense to just look at the estimates that the Zwieback model is giving us. And again, here I'll show you that around the 3rd and the 6th of June, we are seeing quite an increase in soil moisture. And this is represented by the model quite nicely, at least for the maize field. For the wheat field, we're getting not too much difference. It's a very high coherence field. And here, it tends to be underestimated, at least here and this date as well. For the dates more into the vegetation period, we're seeing that there tends to be an overestimation. That also makes sense because there is already vegetation that contributes to the phase, and this is also why we're seeing this spread, so it's not perfectly clustered. The wheat field is a bit more nicely clustered compared to the maize field in red. Sorry, I didn't say it. Maize field in red, and the potato field in yellow. Wheat field is the blue one. And so the model is working to some degree. I think we cannot really say until when the L-band signal still sees soil moisture. I think for this it's quite clear that it's still possible because also it's not that dense, the vegetation. And here with these 1.5 meter maize plants, for example, also the wheat field is very vegetated and could be said that we don't see so much signal anymore from the soil. We can then try to advance it. It's, I think, a very simple approach. So the idea is that the total INSA coherences model is a product of the soil and the vegetation coherence, but we need to weigh it in some way. Therefore, we introduce the mixing coefficient alpha. So we partially compensate for both magnitude and phase. So for example, setting it to minus 0.5 will subtract 50% of the vegetation phase. And in this case, we only model VV. I'll show you in a second why. Parameters, and there's a lot of parameters, and I think we will have to deal with the problem that these equations then are possibly underdetermined. Therefore, I decided to fix a couple of parameters, also because n and h, the density and the height, are contributing similarly to the model. So I fixed the height to 1 and the radius, the plant radius, to 0.02, and the density, so per square meter, plants per square meter, the stock dielectrics, the moisture was varied per time and pixel, and the parameters f, a, and alpha, they were varied globally. So there's only one value in the end. When it comes to cylinder representations, the Bessel series, Bessel cylinders, they are well known, and that's also the model that Virginia Brancato used in her model, but it's very computationally expensive, calculating first order, second order, third order terms. So we decided to use a more simple approach, which doesn't work for very thick stalks. So only thin stalks, but similarly to the Bessel series, infinite in size. And we can also differentiate between VV and HH polarization, which is nice. And the computational cost is quite minimal. So that's like a low frequency infinite cylinder approximation to this full Bessel series. Right, that's our sensitivity, and we can see that for VV we have sensitivity, for HH we don't with the cylinder representation, so it doesn't matter density, height, or moisture. HH always stays flat, but we do have sensitivity with this cylinder, especially for moisture from 0 to 1.5 radians. For height and density we are a bit less sensitive. Right, this is then how our closure phase and our coherence. In the top row here, that's the observed closure phase. and observe coherence. Also some regions here, just to note, that's where the coherence was too low, below 0.35. And all in all, we can say that the model is able to reproduce our observed closure phase and observed coherence. There's some areas, for example, down here where the coherence is estimated too low. Also, sometimes the closure phase is not as strong as it should be, for example. But all in all, we are capturing what we want, which gives us a good basis then for interpreting, first of all, the soil moisture, but also then the estimates. And I just put the estimates of 2 dates here, and that's maybe a bit, I mean, I think there needs to be put more work into the forward model. We do get quite a lot of variation for the vegetation water content, so we can differentiate between the water content between different fields and try to interpret it, but as we don't have ground truth, it's a bit difficult. So that's why I only put 2 maps here. And the estimated, the density, it doesn't vary just looking at this, but actually inside, it's not the perfect range from 0 to 1,000. It does vary a little bit, but not too much, as it's also not as sensitive as N is not so sensitive to the phase. Right, and what we get then for the soil moisture estimates is actually not an improvement. So I also didn't talk about the metrics. Last time it was for the soil moisture model, it was around 0.4, sometimes 0.5, the Pearson correlation. And now the estimates are not better in any way. What we do get is this larger spread. So all this, like everything, all these contributions to the phase from the vegetation, they sort of flatten out. Therefore, these uncertainties, they do translate into our soil moisture estimates, which is actually not what we want. We would want to get these estimates rather into the vegetation, and into the height, into the density as well. And this is not working too well right now. But I think there's potential to this when we refine the method. Do I still have 1 minute? Or is it? You didn't check. I have 2 minutes. Wow, that's great. Yes. I can take this a bit more slowly then. That's our combined Zwieback cylinder model. And as I said, the performance is not improving. But I think in the first place, it's a nice table to compare these 2 different models from Francesco and Simon Zwieback. And we can see, at least according to the validation I did with our bit limited ground data, that for bare soil, the model of Simon Zwieback is working a little better also in HH compared to VV, compared to the model from Francesco here. And when looking at the entire time series, that's these columns and these ones, here actually the model from Francesco, also maybe because of the bigger volume contribution, then there's more vegetation and works a bit better. Right, but here the combined model still is not quite ripe, as the metrics don't really, they don't improve. Right, so in summary, we can estimate soil moisture already. Under vegetation, it's still problematic. We can use cylinder representations, but they don't work for all kinds of vegetation. It has to be vertically oriented vegetation. So with random vegetation, we are still, we still can't really figure that out. But it is at least a start in having a vegetation estimate from differential soil interferometry. And as I said, these ambiguities are a problem also. Just basic forward model development, meaning what structures, what geometric structures we're using, cylinders, or is it other geometries maybe that could help. And this will be investigated further. Also including differential copolar phase differences might make sense because they are very much correlated to wet biomass. And then it's a question of how these complex models, for example, using the Bessel cylinder, can it actually be applied to these large data sets, because the computational cost also in combination with phase triplets, this like quadratic expansion can be it can take a long time for these data sets to compute. Right, that's it. Thanks for your attention.
I think we have time for a couple questions. It's coming from behind you, Marco.
Thank you. So with NISAR, we're seeing a clear difference in the phase, in the interferometric phase between HH and HV. And that appears to be related with precipitation or moisture in general. This is L-band, right? So I was wondering if you looked at the HH minus HV interferometric phase difference, and if you saw any signal or any offsets in the phase.
I mean, so I didn't look at it in particular, just passing by. So I'll just go back to this scatter plot. So I think it can be said that also looking here, there is definitely quite a lot of differences. The differences sometimes are even stronger between HV and HH, for example, compared to the copolar differences. This, I think, looking at this data set can be said, but otherwise I haven't explored these differential cross-polar phase differences and how they, and then also relate to the vegetation estimate. Yeah.
Do we have another question? All right. Thank you, and we can move to Giovanni Nico for our last talk.
Good morning to everybody. So I will try to be fast. So this is the outline of my presentation, which is more focused on in situ data and the comparison with the soil moisture measurements. So I will shortly introduce the study areas, then a few words about the data processing, which is the standard one, and I will focus more on the results, on the comparison with in situ measurements and NDVI estimates. And then in the end, I will try to draw a few conclusions. There are really few conclusions, try to describe way forwards the future work to do, so to speak. So this is the first site. It is in Lisbon. I will call it Espadanal in the rest of the presentation. And this site is characterized by the presence of crops of corns. So we will study the impact of vegetation on the estimate of soil moisture. And at the bottom there is the time series of soil measurements. We installed a few sensors, and so we have this long time series. And here it is just they are just the soil moisture measurements corresponding to the collection of Sentinel-1 data. And okay, just a few data about the kind of sensor that we installed. This is another site in Lisbon. In this case, we tried to compare to study bare soils and also grass, because the results seem to be a little bit different. This is, let's say, a website, a site that we introduced, we use just because a few papers work on this public data set. So we tried to compare also this just to have, let's say, an interface, an osmosis interface with the community. And this is another site in Italy. I'm not going to present all the results. This site is closer to the community of, let's say, working in agriculture. In fact, this is a true experimental site, in the meaning that there are few very small fields with different kind of crops, and we know also the, let's say, the phenological stages of different crops. And what about the data processing? Concerning Sentinel-1, this is, let's say, the traditional interferometric processing that has been used by many of you. And we tried to compute the correlation phases and also let's say the phase triplets. Concerning the multispectral data set, we use also a perspective, but in this case, just we will show the results from Sentinel-2. We estimated different vegetation indices. NDVI seems to perform better, and we use vegetation index not as it is, but we tried to compute the temporal differences in order to catch information about the, let's say, the plant development, the different phenological stages. I start diving into the results. So here is the time series, just a snapshot of the time series of soil moisture in situ measurements. And here we are comparing in blue the interferometric phase closure, and in red and green the phase measurement that has been estimated using two simple models that have been published. DZ stands from Francesco, Desan, and the ZB stands from Zepger. Just to start comparing, we compared, let's say, the phase modeled with the phase measured by SAR interferometry, and also we used, let's say, simple correlation, even if correlation is a little bit weaker in terms of understanding. And in both cases, there is a good correlation, a little bit weaker for, let's say, the model developed by, let's say, published by Zepker and colleagues. But this presentation is not about the models. I will share a few comments about these models later. Now, it is just a way to, let's say, to compare with in situ measurements and also with let's say, the interferometric phase. We did not try to invert the interferometric phase closure because we still need to understand before, let's say, starting the numerical problem of inversion, so to speak. This is an attempt to use the information about, let's say, the vegetation index. On the left, there are the maps around the sensor. The sensor is at the center. Yes, this is the sensor that has been installed at this site, and there is also a comparison. These are two indices, NDVI and NDWI. And in this case, there is a comparison between the interferometric phase, the phase closure, and the temporal change of the NDVI. Here is just, let's say, a comparison, so to speak, even if, again, the presentation is not about the models, between the two numerical models that have been, the simple models that have been used to compare with interferometric phase. And again, we'll present a few considerations because we tried also to compare the two, let's say, phase closures that have been, so to speak, predicted by the two models. And here, there is a comparison with the information coming from multispectral images. Here, we compare on the left, we compare the phase closure with the temporal evolution of the NDVI. And it seems that there is no good, no correlation, not good information can be extracted from this comparison. But if we compare with the temporal change of this index, it seems to be a correlation with the phase closure. And this seems to be correlated to, let's say, to the development of the crop. And when, say, selecting this, the difference of the NDVI, we have also to select one of the three possibilities because we have different combinations, 1, 3, 2, 3, and 1. And 1, 2, let's say, interferometric pairs. And in this case, we are also, let's say, comparing the maximum of this difference to try to, let's say, to catch this information about the, let's say, the development of the plant. And this is another site. In this case, we have grass during the winter season and bare soil during, let's say, the summer season. So it should be relatively simple from the point of view of understanding what is happening with, let's say, the phase closure. In this case, there is no correlation with, as expected, with NDVI, but there is a strong correlation between the, let's say, what has been estimated by SAR interferometry and the model. In this case, I'm referring to Francesco's model, just to, say, to compare the two. And there is a correlation that is negative. It's not positive, like in the case of the vegetation. And now I will share with you a few results that I, let's say, labeled simply as vegetation, in the meaning that they are not sites under control where we installed the in situ sensor. They are just, let's say, fields around our study areas, the two study areas I presented before, where we know what is happening in terms of crops. And the different crops that we are comparing are corn and tomatoes, because they seem to be to have different behaviors. So this is the crop that become quite tall at the end. And okay, some information about the interferometric images, and these are the sites where the pixels have been, let's say, extracted from the Sentinel-1 images. And these are a few results for the corn, for instance. In the case of the corn, we have more or less always the same result, a positive correlation, and it is quite easy to identify that there is, let's say by visual inspection, that there is a correlation between the temporal change of NDVI and interferometric phase closure. And in this case, we have tomato. They say the correlation is a little bit weaker, maybe as expected if we want to take into consideration what is happening with vegetation, because the development maybe is less important with respect to the crop. And it is interesting also these two cases. One is related to the forest, because in the case of forest, there is no temporal change of NDVI. In fact, it seems that the phase closure is not, is not bringing useful information. And also urban areas. In fact, we also use this, this approach to, to correct the biased interferometric estimation in urban areas, as in the second presentation of this session. And now this is the case, the data set of the site of Oklahoma, and more or less we found the same results. These are just a few remarks about the processing that we did. In this case, we use a time lag also till 4 instead of just 3, and these are the Landsat images that have been used to extract the vegetation indices. And we have similar behavior, a little bit less evident, maybe because we know also less about these sites. We simply download the data, we use this public repository. And this is the case, again, grass. This is the information that we extracted from the, let's say, from this repository. So we are always comparing the case of grass, and we notice something that is different with respect to what is happening in, let's say, in the sites that we used in Italy, in Portugal. Is these spikes into the in situ measurements of soil moisture means that there are some difference in terms of the irrigation practice, and so this maybe can also affect the let's say the estimation that is done by let's say by Sentinel-1. And some more results for different sites, and okay, more or less the same result. And now a few words about the models. We use just as let's say, two simple models that have been used in the community. And okay, these are the references for people who are interested in. And this is an experiment that we did with synthetic soil moisture values, so just to keep everything under control. So there is at the beginning an increasing, then let's say a sudden change, and then a stable value, and so on. And there is a good agreement between the two curves, but we have to, so to speak, amplify, calibrate the model that is presented here, that has been, say, developed by the group of Zebker. And we can find the similar, let's say, similar behavior if we set these two constants that are related to the standard deviation of the, let's say, of the scattered signal in this way. There is no reason, but it seems that we have to calibrate if we want to compare the two values. Even if when say estimating the correlation, this is not affected by the value that has been, let's say, found using these two models. So. And we try to use this model further, the model developed by Zebker, because from our point of view, it is important just because it is giving us also information about the depth, and this could be important for this research because it depends on, let's say, in which direction we want to move, which is the community. If it is the community working on climate or the community working in agriculture, because the soil moisture can be, let's say, used say, to be assimilated in a numerical model, but if it should be used by scientists in the plant, working the plant sciences, they want also to know the depth. They are not interested in the top. They want to know what is happening at the root. And from this point of view, this simple model can be useful. It's simply we let's say, estimated the peak in the depth of this, let's say, phase closure for different wavelengths, C and L band, and for the same synthetic data set to just to, let's say, to study the three different segments of this plot, the increasing, decreasing soil moisture, and when there is the jump. So conclusion and future work, so to speak. So for the conclusion, what we found is that in the case of bare soils, we found a correlation with the interferometric phase closure values. Over vegetated area, it seems that we have to add the information about the vegetation. And using just Earth observation data, it seems that there is a good correlation with the temporal changes of NDVI. This is what we found. As a future work, we are going into this direction. First of all, we want to introduce some model that is taking into consideration the phase closure due to the vegetation, due to the, let's say, the different, let's say, the development over the plants. I cited this simple model that has been published recently by Pajo, but so this is the one that we are studying. But there are, we are also trying to borrow something from the community of plant science and using also more advanced models for the soil moisture, so for the soil itself. And this is the paper that we are trying to study, and so the direction that we are trying to follow, where maybe it is possible to introduce some more information and also to compute the sensitivity of soil moisture over the, let's say, the closure phase due to the changes of in the soil moisture. And I think that that is all on my side. Let's conclude.
I think we have a time for a question before lunch, if anyone has one. Yes. Could we get a microphone over there on the...
Yes, thanks for your presentation. Can you go to slide 23? I think it was.
Yes.
Yes. Do you have an explanation why the models seem to, like, the one model goes up and
this is one,
down? And I encountered these switching phases also, and I'm sometimes puzzled why phases switch and suddenly, and I don't understand it.
Yeah. This is was one over the question, because I would expect the opposite if comparing, but say the same function seems to be to give this. I don't know why. The change in the soil moisture is 30%, but this is what we found. Yeah.
Okay. Yeah. Thanks.
Okay, I'll invite everyone to come back after lunch. After the next session, we'll have another of these town hall-ish meetings. See you all later.
alzato. Vai, Giorgese. Sì, era stamattina. No, adesso atmosfera. Scusa, niente. Atmosfera, quindi è giusto, poi di là invece Quentin, Claude, Delgado.
We have several. Should tell me. Huh? This one is one. So people are still coming in. Give everybody an extra minute to settle. But yeah, welcome back. I hope you all had an opportunity to get lunch in time. You're here in a session on atmosphere and ionosphere. There is a parallel session taking place, so welcome back. This is on atmosphere and ionosphere. We have 5 talks, each 20 minutes, and I'll remind the speakers after 15 minutes, we will get up and give you a sign to come to an end, come to a conclusion, so we have time for questions for everybody. 5 talks, so we have enough time actually. And I think we start. David, are you ready to go? Yeah. The first talk is on high resolution atmospheric correction. Of course, for soil interferometry using high resolution ECMWF data.
Perfect. Thank you so much. Very happy to give this talk. This is about Opera's SAR agnostic global tropospheric correction product that is available. I'm presenting this predominantly out of my former role as the Opera project manager. And you can see here also the other contributors from the Opera project, Marin, Scott, Jeremy, and Simran, that have significantly contributed to these slides and the realization of this product. So I just want to put the context, right? We have large-scale initiatives, continental ground motion that is ongoing. Here you can see Opera, and on the other side we have the EGMES component. So really it's driven about the need for trying to get improved ground motion estimates to it. So if you're not yet aware, I do recommend people to go and try out the display portal for the Opera products, and it's pretty consistent with those provided by EGMS currently. But with further ado, really the core focus that I want to focus on is the troposphere. So Opera has created a SAR-agnostic tropospheric correction product. It's globally, in terms of geographical scope, it's available every 6 hours, so every 0006, 12, and 18 UTC. And it's derived from the operational, the analysis product from the high-resolution ECMWF. So really what we're talking about, an 8-kilometer product. It has multiple height levels that we are creating it on, so it's not a 2D product, and I will get into that later on why that is and what it enables. But it's really at the native weather model resolution, and then it's at multiple height levels that span let's say, half a kilometer below topography to ensure you have the minimum topography of the Earth covered. And then it goes up to the height elevation of the weather model, which is about 80 kilometers. And you can see it has 145 different levels. So really, it enables you to do spaceborne. It doesn't matter if it's P, X, L, S, etc. It's a non-dispersive component. And then in terms of airborne, that's also enabled, and we will show you some examples down the line. The format itself is a cloud-optimized NetCDF, so you can easily slice and dice through it. All the products are free and open, available through the NASA archives, and the latency is about 2 to 3 days. And the reason for that is that ECMWF, it's a commercial entity. You cannot use the products directly and put it under a Creative Commons license. There is an embargo for at least 24 hours. So why a 3D zenith tropospheric delay? So we had initially at Opera, it was to be the product that was to be embedded with the displacement product from Sentinel, and we were going to do the same for the NISAR product. But it was a nice opportunity for us to take a step back and reevaluate whether or not we can enable more by staying in the zenith. So if we're talking at about a 9-kilometer spacing of the weather model, and we're thinking about the tropospheric thickness, we wouldn't be crossing more than 1 to 2 voxels of the weather model in terms of the ray tracing. So really, we did the analysis, and there is not a significant loss in terms of projecting it versus doing the actual tracing along the ray. So that holds for this 9-kilometer model. That doesn't hold for a higher resolution model, of course. Then the other thing is, why are these 3D cubes and not 2D fields? Well, the real resolution of the model, I mean, it is its native resolution is 9-kilometer. Where we get higher detail in the troposphere is generally when we intersect it with topography, and you get the topography correlated components. So really, at that point, you have introduced additional information. And what we are doing here is adopting what NISAR has done for its geometric fields, is you stay at this coarse resolution, you provide it at the vertical levels, and then the user will do the intersection themselves. So that means that we can directly have the same volume, but we directly also enable the airborne component. And if other applications exist where users are not interested at intersecting at the topography, but at a fixed height level, it's pretty much usable for that as well. So let me see. So Radar is actually the underlying package that we are using for doing this. This is a Python-based package. Let's be honest, the troposphere is not the most complicated equation to calculate from. It's an integral of the refractivity. So it's just an efficient implementation, I would say. At the native weather model grid nodes, we try to limit as much as we can lateral interpolation. There have been studies done by ECNWF for ESA that just shows that you introduce easily 15% error by go ahead and doing so. But if we're thinking where this package is currently being used, it's being used in the AREA project for the GAN-W products that are available at ASF DAC, but also the Opera project made this routinely available product, and it's also the underlying code is what gets used for the NICER tropospheric correction layer. So this is an open source package. Anybody can go ahead and try to use it. It supports other models, so if you're really interested in high resolution, it's also the high resolution rapid refresh in the US, or you can fall back to reanalysis products, etc. So here I just want to show what we already know. So it's a 10-year or a 9-year record of GPS zenith tropospheric delays. If we just calculate the mean and we show that on the map, you approach here the mean delay. So the ranges are what you expect, around 2 meters, 2.5 meters, fully correlated with topography because it's less propagation to the top of the mountain as it would be at sea level. So that is kind of what we have from the GPS. We know it's in the order of 5 millimeter to 1 centimeter accuracy, and that is the signal that we of course want to remove. But when we're looking at INSAR, we're looking at variability. So let's say the standard deviation of all these delays, that is what we're trying to correct. So I call this the target or the signal to correct for, and it's generally, you can see here this color range, it goes pretty high up depending where you are, but at about 10 centimeters is the variability. So that's from one day to another in terms of standard deviations. So if we use the tropospheric correction from Opera and we compare this against the GPS, so we calculate the residuals, and then we take the standard deviation again. Ideally, if you would do a perfect correction, and let's assume that the GPS would be fully correct, you would see this fall down to 0. The GPS has its own uncertainty, but also the model is still a model and has also its limitations. But what do we see here, and this is the same color bar as before, where you remember the target signal could go easily up to 10 centimeters. Now we're in the range of about 1 centimeter to 2 centimeters in terms of the residual of the noise. So this analysis, of course, is done at GPS stations. The station's distribution is probably 20 to 25 kilometers if it's very dense. It's not doing the higher analysis. For that, you would compare interferograms, for example, but it's the length scales of 25 kilometers and longer that you currently can kind of see in this plot. A key observation is that these residuals do not correlate with topography. So it's the model is predominantly doing a decent job, and it doesn't have topography correlated bias left in there. But one thing that stands out is that the variability over, for example, Europe is smaller. So clearly the ECNWF model is doing a very good job. You kind of see a little split here over North America. The hypothesis which we are still kind of looking into it is that this is related to the low-level jet streams that is transporting moisture and water vapor from the Gulf of Mexico inland. So there is still some larger residual signals. Now, if we want to put this in a more physical context, weather models are often dependent on the climatic zone, the type of surface that we have, if it's arid or tropical. So the blue bars here represent the signal, and then you can see the orange kind of shows you the reduction. In the background, you see 3 colors, green, yellow, and red. And that really gives a constraint whether or not we had enough data to say something about it. But on average, we see about a factor of 6 reduction capability. Here you can kind of see it per climate type. Tropical, generally, if you look here, tropical, which is the green, is not very well sampled in the data sets that we have. But that's where you would typically see the deep convection that are more challenging to constrain. Still, it's pretty decent reduction. Arid and temperate and continental, that's where we have the decent GPS coverage to say something about it. And again, arid, it's pretty low integrated water vapor. We're looking more at the hydrostatic component, so we know that models do that pretty well. And then here you have the temperate, where we believe that it's the dense radio sound data over the US as well as Europe that are constraining the models pretty well. Polar, I mean, I think there's like 40 stations, so can't really say anything conclusive about that. So the next set of slides are just giving you illustration. I mean, it's not dependent on the frequency, so we can apply it to P-band, X-band, L-band, etc. So here's an example of biomass. It's a level 1C product where the interferograms are already embedded in it over Peru. Generally, if you look in the center of the image, and after we see a slight reduction, and I'm not saying that these weather models are the holy grail of things either. We will come to a discussion slide on that later, but they do tend to, for more than half of the cases, improve the results. Another example here is for the NICER GUN-W product. Here it's about a 250 kilometer SWAT. Again, it's left-looking, which is different from the other typical sensors. The tropospheric correction here in New Mexico, it's pretty much elevation correlated. Again, this is like a poster child illustration of things that are going to go relatively well. Another one here is provided by Scott Stanowick. This is for Capella. A couple of unique things about Capella, of course. Here it's a very narrow SWAT, 10 kilometers. And also this is in a on average 3-day repeat, so there is a shift in the UTC timing. So you can round to the nearest time, you can do temporal interpolation. Scott did a linear interpolation in time here. But again, you have the original one. This is for Piton de la Fournaise in La Réunion, and you can clearly see the signal after correction and a strong reduction in the topocorrelated signal. Another example here is for UAVSAR. This is the baseline uncorrected data. I just wanted to illustrate you that you can do the different height levels. So given that the height levels of the three-dimensional cube are there, you can also take the height level where the platform is flying on and subtract that back off of your data. And then you can just project it again along the incidence angles, which are relatively large for UAVSAR. And here, this is pre-baseline corrected, so you kind of see a large gradient there. But at least after correction, you see that more of a incidence angle variation on the baseline. So, and with that, I do think that we should be doing the corrections before baseline analysis, and so that we don't have any contamination. And here's another example where you can clearly see these two mountain ridges. And this is the Big Sur, where we had a large landslide a while ago. And you can clearly see also the reduction in the data here. So the tropospheric corrections are available online. That doesn't mean it's very easily accessible. We have done the work to integrate this in a PR for MinPy. So MinPy is widely used in this community, developed by Yunjin, Haresh, and also with Falk. And there is a summer course coming up, so I would recommend you all to register for it. But really, this is where I want to call the attention to, where it's integrated as a tropospheric correction method, and ultimately that will do for you all the slicing and dicing of the data, fetching it from the archive, etc. So before that, I was only showing you interferogram individual ones. This is the application to a NICER time series over Mexico City. We can easily see about 20 centimeters of motion per year. And then if we look at what the troposphere in terms of impact had when we did the corrections, we're looking at about an 8 centimeter per year impact. And that is what you can expect for a short duration time series. Atmosphere can directly, it's not yet averaged out, so it's still pretty significant. I also want to say that NICER does have its own tropospheric correction, and that is consistent between OPRA and NICER, so we're pretty happy that I didn't show any issues. So I briefly want to end with 2 slides. One is discussion and the summary. The discussion here, do tropospheric corrections always work? I mean, they are a model, and models do have their varying performance, and it depends on local dynamics and physics. So it's an active field of research, but I would argue that on average, the models are improving, I do think have value to integrate. Now, are higher resolution models better? It's where you can introduce signals. So we know that models are generally good at capturing the long wavelength signals. That's pretty consistent between the models. But if you have higher resolution, you can capture these local dynamics and the hydrostatic variation more, perhaps potentially better, but also the water vapor variations could be potentially off, and at that point you would be introducing high frequency noise. So the timing is very important, and I would say that's where you still look on a case-by-case basis. But in terms of expected benefits, it reduces the noise in the time series, it improves the analysis and detection of small magnitude signals, and it can help you for localized studies. So coming down to the summary, so Opera has released a Tropo product. It's derived from ECNWF high-resolution data for every model epic. It's a latency of 2 to 3 days, and it's a 3-dimensional cube. It's SAR agnostic. We demonstrated it already to different missions. And it's generally, it's fully integrated now in MinPy and ready for the community to go ahead and use. And I will leave it there and take any questions. Thank you.
Thank you, David, for this nice talk. We have time for questions. Ivana? Oh, yeah. Okay. So we start with Christoph.
Okay, then maybe I go first, yes. So thanks for the talk. Quick question on your comparison against the GNSS. So for that one, did you use your kind of original product, which requires a downward continuation to the GPS station, or did you run the program for the very position of the GPS station for the comparison?
So this is the, so I didn't go and attempt to do what the GPS community does best. So we were using the off-the-shelf products provided by UNR. And that's a dedicated Zenith tropospheric calculation. So it's not part of the positioning, it's its dedicated pipeline to compute those.
I'm asking, let's say, about your side of the solution. So you have the Opera package, which gives the troposphere in this layer-based solution, which stops, if I read it correctly, 500 meters above ellipsoid, something like that.
Yeah.
So did you extend that one and compare it to the GPS, or did you do a specific processing with your method for the GPS position?
So we calculated all the delays, and then we just intersected it at the GPS locations, which has a XYZ, and that then becomes the estimate for the GPS because it's a Zenith delay at that height level.
Okay, so sometimes you have to kind of downward extend your solution, upward interpolate, so to really get at the level of the GPS station. Then.
Yeah, so you have these different layers, right? So 100 plus. So we would always take the layer beneath it, the layer above it, to get to that height level. And I think we're doing linear in the vertical, and it's a bilinear in the horizontal.
Okay, yeah, thanks.
Yeah.
If I understand well, the temporal resolution of this correction is 6 hours, right? And when you correct the INSAR products, you use the, let's say, closest sample in time to the SAR acquisition time.
Yeah, so I mean, two schools of thought here, right? So you could do the interpolation in time. I generally have found that even the nearest time, it's still pretty good. And I think there are publications out there that argue what is the temporal decorrelation of the troposphere. And I think within a couple of hours, you should still be fine. And also, I mean, the wind speed moves at different times, so at different height levels, it's different wind speed. So linear interpolation will still be an approximation. And if you look at the high resolution being outputted every hour versus you doing a linear interpolation, it almost gets to the similar results. So I got more lazy and started rounding to the nearest time.
Okay, no, because in my presentation after I discussed this problem, so I just want to, okay, thank you so much.
You're welcome.
Thank you. Any more questions?
Is related to the previous question. Okay, the correction time depends also on what is happening at the steering level, in the meaning that if there is a wind at that level, this is changing the mass of water vapor. So you can see different things depending on this. So maybe okay, this could be relevant in some cases depending on, let's say, the local configuration.
Yeah. So we provide it at the native weather model grid nodes at almost the native weather model height level. So we're trying not to introduce fabricated data. So we look globally what are the height levels because they're at model levels, they're not at pressure levels. So that's the one thing that we do. And then it's at the fixed UTC epics. So it allows the community to try and do different flavors if they want to use the height, the velocity of the surface winds or the winds at a certain height level, they could potentially do that. But it's not something that we predetermine for the user to do. But it could be. I'm not sure if it will add beyond going into investigations on it. Yeah.
Okay. Thank you, David.
You're welcome.
I think we have to move on. Our next talk is on the use of cheap GNSS receivers for INSA, given by Amgad Abasid. Amgad Abasid, did I pronounce?
Yes.
Almost correctly.
Correct, yes.
So you have a button and switch. Go ahead.
Hello, everyone. My name is Amgad Abazid. I am a PhD student at AGH University of Krakow. Today, I will present my research on low-cost GNSS for INSAR atmospheric correction, assessing Zenith tropospheric delay accuracy. As we know, atmospheric delays are the main obstacle to achieving millimeter level accuracy for INSAR deformation measurements. Tropospheric variations induce phase noise that mimics surface displacement. So to improve the reliability of INSAR observations, independent tropospheric corrections are required to use. A highly effective solution is using a global navigation satellite system. GNSS provides continuous Zenith tropospheric delay estimation by interpolating ZTD values from a GNSS network. We can correct INSAR images. However, geodetic GNSS receivers are expensive. It costs between $10,000 and $20,000. Which restrict the densification of GNSS networks. Recently, low-cost GNSS receivers emerged as alternative solution for geodetic receivers with a fraction of cost and comparable performance. This figure shows the evolution of low-cost GNSS receivers. In 1982, the first commercial GPS receiver has been introduced to the market with cost more than $200,000. Then the cost of geodetic receivers decreased to $10,000. In 2018, U-Blocks introduced ZF9P, the first low-cost dual-frequency GNSS receiver. And currently, we can buy a low-cost GNSS receiver, can provide centimeter accuracy for only $100. For using low-cost GNSS for estimating Zenith tropospheric delay, Dabov and Bagheri compared the performance of geodetic receivers and low-cost receivers for estimating ZTD values. They reported that the difference between low-cost receivers and geodetic receivers for estimating ZTD values within a few centimeters. They used precise point positioning with float ambiguity. Until now, there is no study evaluated the performance of precise point positioning with ambiguity resolution for estimating ZTD values from low-cost GNSS receivers, which expected to improve the accuracy of ZTD values. So the main objective of our research is examine the accuracy of precise point positioning with ambiguity resolution using low-cost dual-frequency receiver for tropospheric delay estimation. Also, the second objective is evaluate the potential of low-cost receivers to densify atmospheric monitoring infrastructures for inter-atmospheric corrections. To perform the experiment, we processed the data from 3 low-cost course stations from Centipede RTK network, in addition to establishing a low-cost station at Aswan city in Egypt. The observation duration was standard for 3 days with a session length of 24 hours. But for Aswan station, the session length was 3 hours. The sampling rate was 30 seconds. This figure shows the location of the 3 low-cost course stations from Centipede RTK network in France. And the second figure shows the location of the low-cost station in Aswan city in Egypt. All receivers used in this experiment are low-cost receivers from U-Blocks ZF9P. The data processed from GPS and Galileo, and we used the final precise orbit and clock products. We used the net difference software to process the data and CSRS PPP online surface. This figure shows the geodetic receiver and the low-cost receiver at Aswan station. This table shows the root mean square error for ZTD values estimated by the low-cost receivers compared to geodetic receivers. As we can see, the root mean square error within millimeter level, the lowest RMSE value is 2 millimeter, and the highest RMSE value is 9 millimeter. Also, the last column shows the fixed rate for each station. As we can see, there is a high fixed rate for for all low-cost stations. This figure shows the conversion of the ZTD values estimated by the geodetic receiver and the low-cost receiver at the first station. The horizontal axis represents time in hours, and the vertical axis represents ZTD value in millimeter. ZTD values estimated by the geodetic receiver represented by a red line, and ZTD values estimated by the low-cost receiver represented by green dots. As we can see, there is a strong correlation between ZTD values estimated by the geodetic receiver and the low-cost receiver, with differences at millimeter level. This is the result for the second station. Also, as the first station, there is a strong correlation between ZTD values estimated by geodetic receiver and the low-cost receiver. And the difference between both receivers is less than 1 centimeter. This figure shows also the result for the third station. Although there is a systematic difference between low-cost receiver and the geodetic receiver, the difference is still generally less than 1 centimeter. And this figure shows the ZTD values estimated by the geodetic receiver and the low-cost receiver for Aswan station. As the previous stations, also there is a strong correlation between ZTD values estimated by the geodetic receiver and the low-cost receiver, and the difference between both receivers within millimeters. The conclusion of this study, the first conclusion is the low-cost DNS receivers successfully achieved the fixed ambiguity solution for a substantial portion of the observation period. When compared with the geodetic-grade reference systems, the xenotropospheric delay values obtained from the low-cost receivers agreed closely with the root mean square error ranging from 2 millimeter to 9 millimeter. Integrating low-cost GNSS into NSAR workflows enables dense, cost-effective monitoring networks. Thank you for your attention.
So, thank you very much for this talk. I'm sure there are questions. We have time. Christoph?
So yeah, thank you very much for the talk, and very happy to see that even now with, let's say, $100 instrument, we can kind of solve on a point-wise basis the troposphere. My question is, do you have any plans, let's say, of connecting your work with the SAR specifically, let's say, like helping a specific, let's say, calibration side of things? I mean, if I hear this, even installing a corner reflectors costs us usually several hundreds to thousands of dollars, so just spending another $100 more for a decent GPS for calibration sites, I believe this would be a viable investment probably. So do you have any plans of, let's say, connecting your work with the SAR community in certain ways?
With NSAR?
With the SAR community, let's say.
Yes, of course. This research is ongoing research. Actually, we applied for a fund 6 months ago and get a fund. We will extend our research at a field with ground deformation. We will fix some low-cost station and monitor the ground with NSAR also.
Okay, yeah, thank you.
So maybe I have an additional question. I mean, you're talking about millimeters. In comparison, so I have actually two questions. First of all, the difference 5 to 8 millimeters is already close to the models we have. In the talk before, we had about 10 millimeters to global models, so where you don't need a GPS station. On the other hand, 3 to 5 is small compared to the geodetic one. Do you know which one is right? Do you have any other means to compare the geodetic values or to validate, to make sure that this is a correct reference?
Actually, the main objective is to show we can replace the geodetic with low cost. We don't have more precise reference data than geodetic, so we use the geodetic for conversion. Also, some places like my country, Egypt, we have actually a GNS network, but not a global network, not connected to the global network. So we can use geodetic receivers to densify the global GNSS network.
Thank you.
Thank you very much for your talk.
Thank you.
I had one question. So you had those reference stations and then your low-cost receiver. There appeared to be a bias on the second station. Were they processed consistently, or sometimes it has to do with the network adaptation on the integrated water vapor component?
Actually, I don't know the reason. We tried to investigate why this error evaluate, but it need more work to define why is this difference.
Okay, thank you. Okay, any other questions? Then thank you very much.
Thank you.
Okay, then we have our next speaker for dispersive ionospheric phase estimation in L-band INSAR using Fourier neural net operators. That's by Kazuki Yanagiwa. Floor is all yours. Thank you.
Yeah, Yanagiya. Thank you. Thank you, Chairman. I'm Kazuki Yanagiya from Earth Observation Research Center, JAXA. So today I will talk about the deep learning model for estimation of dispersive ionospheric phase in L-band INSER. So as you already know, the ionospheric pulse delay phase is a major phase component in INSER, and it is especially important for long wavelength L-band missions because the ionospheric phase is irreversibly proportional to the microwave center frequency. So these are the examples of the JAXA's L-band ALOS2 interferograms with ionospheric phase. So if we want to detect ground deformation accurately, we need to detect and correct those ionospheric phase precisely. Yeah, and one standard method is a correction method is the range split spectral method. I will call SSM in this presentation. And SSM can separate the ionospheric phase from a range subband interferograms using its frequency dependence. But in practice, SSM is sensitive to the input, phase noise of the input range subband interferograms. So we need to smoothing before and after the SSM calculation. So therefore, various improved methods have been proposed to achieve more accurate estimation under noisy condition. So the main question of this, main research question of this study is, can deep learning model this SSM process, including pre and post smoothing steps? Okay, so let me show you the training and inference framework with deep learning. So we first generate the simulated interferograms from a phase, synthetic phase component. It includes the reference ionospheric phase. Then we input those simulated interferograms into the deep learning model. And then we trained this deep learning model to minimize the difference between estimated ionospheric phase and reference ionospheric phase. And we update the model parameter. And finally, the trained model is applied to real interferograms to estimate the ionospheric phase. So in this study, we use the neural operators instead of classical neural networks. Neural networks is a powerful approximator of functions, and the neural networks can learn the mapping from discrete value to discrete value. However, the neural operators can learn the mapping between the functions. In other words, it can learn the mapping from continuous field to continuous field. It is one of the important features of the operator learning. And especially, we use the Fourier neural operator in this study, FNO. FNO is one of the neural operator model that uses the Fourier transforms to model operators between functions. And FNO was originally proposed and developed for the first surrogate model for partial differential equation-based numerical simulations. So the left panel shows the example of the simulation of Navier-Stokes equation using FNO, and the right panel shows the example of the geoscience. The spherical Fourier neural operator model is used for a weather forecast simulation by NVIDIA. So FNO learns a parametric operator that maps the input function space to the output function space. So this is the schematic image of the FNO model. And FNO first lifts input to the higher dimensional feature space. And then FNO applies the spectral convolutional layers. It is called as a Fourier layers. And finally, it projects the features back to the output space. So actually, our study target is not a partial differential equation, but we use this FNO model to map a noisy unwrapped subband interferograms to a noise-free unwrapped ionospheric phase. So this is the schematic image of our proposed model. And the important point is the spatial size. It is written by M by N. in this image. The spatial size of input data and each intermediate features are same from input to output. It means this model can handle the data with different spatial sizes at inference time. And the model training and evaluation were conducted on GPU workstation at ERC. And the open source neural operator library, which developed by the authors of first FNO papers, is used for model implementation. And all training, validation, and test data were simulated interferograms. This allows us rapid generation of large ground truth datasets without manual labeling, because usually the labeling is use a lot of time and human resources, so it is an advantage. But in contrast, there may be some gap between simulated data and real interferograms. It is called domain gap issue in deep learning. So it can limit estimation performance. Okay, so let's move on how we generate the simulated interferograms. In this study, the unwrapped interferometric phase is modeled as a linear combination of 4 non-dispersive components and 1 dispersive ionospheric component. And non-dispersive components include the ground deformation phase, a turbulent tropospheric delay phase, and stratified tropospheric delay phase, and long wavelength trend. So we generated these non-dispersive components with a variable random parameters and according to this simulation method. And we also simulated the dispersive ionospheric phase from the total electron content TEC field. So sometimes ionospheric phase modeled as a second order or third order polynomial empirically, but in this study, we would like to simulate more natural and more irregular spatial pattern of ionospheric phase. So we simulated from TEC field as a superposition of plane waves. And the wavelengths were randomly chosen from 100 to 1,000 kilometers. It is a typical scale of MSTID and LSTID. And after that, we can calculate the difference of simulated TEC anomaly field. So this is the example of delta TEC, simulated TEC, delta TEC. And then we can convert delta TEC to the ionospheric phase according to this equation. Okay, after generating those phase components, we combined those components with random weight to generate various synthetic high and low band interferogram phases. And the simulated interferograms were normalized to the range of -1 to +1 to improve the training efficiency. And to make the subband interferograms, we use the fixed frequency values corresponding to the ALOS to 3-meter data, because we want to test this model using ALOS2 data. And finally, we added the synthetic noise up to 80% of the simulated image, such as a random small area offset and random noise and no data areas. Okay, so let's move on the result of model training. So this panel shows the mean squared error loss of training and validation of model. The blue line shows the training loss, and red color shows the validation loss. And both MSE losses decreased and converged to similar values over 100 epochs. So we decided to use the model at the final epoch for test and inference. And this is the result of the test in simulated interferograms. The proposed FNO model accurately estimated the ionospheric phase on 10,000 unseen test simulated interferograms. So this is the one example of the simulated test interferograms. This is the high band simulated interferogram and with a noise and no data areas. And this is the true ionospheric phase contained in this one, and this is the estimated result by the FNO model. So FNO can estimate the noise-free ionospheric phase from this noisy simulated data. So we then evaluate whether this model generalizes across the spatial sizes of input data. So although this model was trained on 256 by 256 pixels data, the model can successfully estimate the ionospheric phase contained in the simulated interferograms, which sizes from 32 by 32 pixels to 2048 to 2048 pixels. So it means the model can be applied to the different size of input data. And this flexibility is one practical advantage of the neural operator model. Okay. So we also validate using scalar values. We input the scalar values to the trained model and compare the output with the values derived from the theoretical equation. So this is a result of comparison. The estimated ionospheric phase value agrees well with the theoretical values. So it indicates the FNO model can learn not only the spatial feature of ionospheric phase, but it can also learn the mapping based on this theoretical equation. And it is another advantage of the operator learning. Okay, so let's move on the validation using real ALOS2 interferograms, because it is very important, because sometimes deep learning model can be applied to the simulated data, but it cannot be applied real data. So this validation is very important. We validated with the three regions data, northeastern Siberia and Noto Peninsula, Japan. This image contains the cluster deformation with the 2023 earthquake, and Shikoku Island in Japan. And these are the result of estimation. The upper and middle lower rows indicate the Siberian, Noto, Shikoku results. And this is the coherence of high band interferograms. This is the full band interferograms. And this is the ionospheric phase estimated by a classical split spectrum method. And this is the result estimated by the trained FNO model. And these are the non-dispersive components corrected by each method, SSM and FNO. So Siberian case and Noto case indicates the trained FNO model can successfully estimate the ionospheric phase. Even this model is trained only simulated data. However, the Shikoku case, this lower low, the FNO model can only estimate the broad pattern of ionospheric phase compared to this SSM result. The Shikoku case included the localized ionospheric disturbance with a spatial scale of about 10 kilometers. It is reported as a daytime sporadic E by previous study. So this spatial scale is far smaller than the training condition. So we think it is a major cause of the degraded estimation accuracy. Okay, so to improve the model flexibility, we modify the model by explicitly taking frequency values as input. So by input these frequency values, this improved model can be applied different frequency conditions and, of course, different L1SAR data. So we tested with NICER data. We use a NICER pre-calibration data from Ethiopia. And of course, my center frequency and the bandwidth is different from ALOS to 3-meter data. And this is the high band coherence. This is the full band interferogram. This is the ionospheric phase derived by classical SSM, and this is non-dispersive from SSM. And this is the estimated result by improved FNO model. But this is a preliminary result. But yeah, by providing frequency information as an additional input channels, the improved model can be applied to data taken by different frequency conditions and different L-band satellite. So this is the final result of this presentation. We also tested with the ALOS2 scanner data, because scanner data is the most difficult target. The bandwidth is very narrow, only 11.9 megahertz, and the noise of the subband interferogram is very high. And also, in this case, this data is taken around the Mackenzie Delta in Canada, Arctic region, and the ionospheric disturbance is very heavy. And also, we collected the azimuth streaks using a pixel offset, but as you can see, some azimuth streaks remains in the interferograms. And this is the full band interferograms of the scanner. This is estimated ionospheric phase by SSM, and this is a non-dispersive SSM. Yeah, in this case, SSM cannot accurately collect the ionospheric phase. And this is the estimation result of FNO, improved FNO model. Yes, FNO model can estimate the broad spatial pattern of ionospheric disturbance, but it cannot estimate the local small-scale structures, same as a Shikoku case. So it is the current limit of our model, so we will improve the model to these local and small-scale structure. Okay, so let me summarize this presentation. The FNO surrogate model learned both spatial patterns of ionospheric phase and the theoretical relationship of the SSM equation. And it generalized from simulated interferograms to real ALOS2 and nicer L-band interferograms without any retraining and fine-tuning. Yeah. However, the performance degraded for unseen, localized, and small-scale ionospheric disturbances such as sporadic E and azimuth streaks. So in future works, we first will try to simulate those local scale, small scale structure of ionospheric disturbances. And also we will try to use the physics constrained and physics informed models, PINO, and also we will test more recent advanced model, U-shaped, such as U-shaped FNO and local FNO. So my colleague, Dr. Shigemitsu, will present the other machine learning technique, independent component analysis, to decompose DEM error and ionospheric delay phase in this evening. So if you're interested in this presentation, please come to his poster. Yeah, thank you for your attention.
Questions? Thank you very much.
Thank you for the great presentation. I was wondering how much time does it take to use the FNO method compared to the SSM method? And I imagine you also need a graphics card to evaluate the network. Thank you.
So you mean how much time take for estimation?
Yes, yes.
Yeah, it takes a lot of time for model training. In this case, it takes 8 hours with our small workstation environment. But when once finished the training, the model can estimate the ionospheric phase using 1 to 2 seconds. So for the inference stage, it takes a few seconds, yeah. And but we should prepare the range subband interferograms, and we should conduct unwrapping. So it takes a lot of time. Yeah.
Thank you.
Thank you for presentation. If I'm right, you are training the network to predict the high and low subband interferogram, and then use it for ionospheric calibration. Is that the case? If so, then I was not clear actually how this is give any advantages over the spectral spectrum approach or standard SSM approach.
You mean the advantage of this deep
Yeah,
learning
the
model?
network. Because if you have a relatively good bandwidth, then you can estimate low and high subbands.
Yes, one advantage is the current split spectral method is the need the smoothing steps, and in the case of heavy noise data, the smoothing parameter is very important. If we change the filter size and the threshold of the outlier removing, the result will be changed easily. And this deep learning model doesn't need to set a parameters in the inference stage. So we don't need to, we just input the noisy data and output the noise-free unwrapped ionospheric phase without any parameter tuning. It is one advantage of this deep learning model.
Okay, just a last curiosity. I wonder if you have tested with the biomass data sets, because you have relatively really small bandwidth biomass data, like if I'm not wrong, 6 megahertz.
I have not tested with the biomass data, but if we try to, if we test the biomass data, we have to train the P-band frequency with this model. Yeah, but we can.
Thank you.
Yeah.
Okay, thank you again.
Good afternoon. In this presentation, I'll try to propose a new algorithm to solve several problems connected to range split spectrum method for the range phase, ionospheric phase retrieval. Just a few words about outline of my presentation. Yes, let's start with the L-band data exploited for this work. Then I show you, as already said by the previous speaker, some the effect, let me say, of the ionospheric effect on the L-band INSAR analysis. Then I'll focus my attention on range split spectrum method for the ionospheric phase retrieval and removal from the INSAR analysis. And then I focus on the criticalities of the RSS-based method. And then I'll focus my attention on the prime RSS, that is the algorithm that we proposed to solve several problems connected to the range split spectrum. Also in alternative formulation of the range split spectrum method. Okay, so several results and final remark. Let's start with the data set that we exploit for this work. We use a Saucon 1 constellation, that is an Argentinian constellation composed of two twin sensors, Saucon 1A and Saucon 1B, with potentially 8 days of revisiting time. We benefit from the Italian Space Agency zone of exclusivity, that is essentially the entire Europe, where the Saucon 1 constellation acquire in a systematic mode and interferometric mode, actually a StripMap mode, with a resolution of 10 for 5 meters, with a footprint of 14 to 60 kilometers, and of course it's a L-band system, so we are talking about 23 centimeters of wavelength. So just a few words about the ionospheric effect in the DINSAR application. We have dual effect in azimuth direction and in slant range direction. The first is essentially due to the fast variation of the ionosphere within synthetic aperture antenna that produce a shift of the pixel. Of course, you have a different shift between the primary and secondary image, so when you perform interferometric analysis, you have a sort of, you lose coherence, interferometric coherence. There are several techniques proposed in literature to solve this problem. The multi-aperture interferometry or pixel offset tracking to estimate the shift and compensate in a co-registration phase, or for example, a refocusing procedure that try to solve the problem from the beginning. And then we have the slant range direction, and we benefit essentially for this component in dispersive behavior of the ionosphere. So one of the most important approach for estimation of this component is the range split spectrum method. Okay, so this is just a few words about the azimuth effect. This is the problem due to the shift of the pixels. You lose coherence. You have this strip, a very long strip in the azimuth direction where you lose coherence. And we solve in this case by using pixel offset tracking that the shift estimated is used in the geometrical co-registration, and so we gain coherent, interferometric coherence. This is our starting point because, as I said, we want to focus on the range ionospheric phase component. Okay. As I said before, we benefit of dispersive nature of the ionosphere by using essentially this very simple model proposed in this paper, where the interferometric phase can be divided essentially in non-dispersive and dispersive component. By splitting the range bandwidth in 3 slices, okay, you can generate a low band interferogram and high band interferogram to generate essentially a system of 2 equations in 2 unknowns that you can solve in a very easy way to generate essentially the estimation of non-dispersive component and dispersive component connected to ionosphere. Okay, we will prefer to express everything in function of wavelength, but it's essentially the same if you express with the central frequency. Okay, so the ionospheric phase component is essentially composed of 2 terms. The first term is the raw ionosphere that is generated by the difference between the high band and low band in interferograms. Okay, this is an example. As you can see, this the raw ionosphere that has is a very small signals. Okay, slowly variable with a ramp-like behavior. And there is another term that is a ionospheric extraction factor that is this very big real number. And the problem of range split spectrum is essentially, we have 2 kinds of problems. You have the problem of the phasor wrapping, because, for example, in this expression, you need to unwrap at least one of both interferograms, because you have to multiply this for a real number, that is the ratio between low and high wavelength. And another problem is the multiplication for this amplification factor that is very big, minus 43.41, for example, for SOGOM 1. Indeed, if we multiply and use this formulation as is, and we multiply this factor for the raw ionosphere, and we wrap, this is the result. This is not our discovery, of course. This is well known in literature, so it is essential to implement the filtering procedure to solve this kind of problem, to extract the ionospheric phase from the noise, let me say. And so this is the prime RSS algorithm. Essentially, the RSS technique does not prevent us to properly select the low band and high band. Okay, of course, we need to separate, we need to a distance in spectrum, but essentially we can properly select the lambda low and lambda high to generate an amplification factor that is an integer number, as close as possible to an integer number. But not any integer number. We want that this number is divisible for an high, small number, prime number, 2, 3, and so on. For example, in this case, by selecting this lambda low and lambda high, we obtain 48, that is essentially 2 to the power of 4 for 3. Why this? Because in this way, we can benefit of a new degree of freedom that we can use to generate an iterative procedure. Because now we don't multiply for a big number, we can multiply at each step for small number, for 2, for 2, for 2, for 2, and then for 3. Of course, at each iteration, you need a filtering procedure. And RSS and the prime RSS algorithm implement also another strategy. Okay, we essentially benefit of the behavior of the raw signals, of raw ionosphere signals. That, as I said before, is lowly variable and ramp-like behavior. Okay, so if you put the raw ionosphere within a complex exponential and you Fourier transform a complex exponential, you essentially emphasize the principal component of the ionosphere, let me say. And then when you identify in the power spectrum density, the peak of the power spectrum density, you can apply a narrow band filter to remove essentially the noise. In other words, we can move from this spectrum here, okay, that is the raw ionosphere, and after by applying the filter, we remove the noise. In the first case, you have the energy spread in all your spectrum essentially, okay? So how it works? We start from the raw ionosphere. Okay, we put this in a complex exponential. We apply the filter. Then we multiply the results for 2. Okay, we apply the filter. Then we multiply it for 2 again, apply the filter, and so on. As you can see, the signal rises from the noise essentially, and we filter out the noise. We multiply for 2, then for 2, and then for 3. And this is the interferometric phase, okay, and this is the ionospheric phase that we use, that we estimate essentially, and this is the results after the filtering procedure. And if we compare, for example, with other approach that usually a spatial approach, filtering approach, you can, as all spatial filter, you may have some artifacts due to the fact that you have a lot of noise, and so you have some problems along the edge of the interferogram, along the area with the more decorrelated area. And so you underestimate several ramps. You have some artifact here, some artifact here, and this has been generated with a very exploited software that is ICE, okay, in a standard configuration, of course. Okay, now let's move to another formulation of range split spectrum that is proposed several years ago. It is very interesting because in the ionospheric phase, okay, this is only the final results, but essentially the ionospheric phase is composed of not only low and high interferometric, low band and high band interferograms, but include also the full band interferograms, properly weighted with these two terms, X and Z. And in this paper, they benefit of the fact that these terms here is more or less 0.5, so they multiply for 2, okay, to retrieve 2 times the ionospheric phase. But the advantage of this formulation is that you don't need a wrapping. Why? Because here you have the full band phase, okay, multiplied for nothing, and then you have these terms here that in the reasonable hypothesis that the difference between low band and high band interferogram is already unwrapped, you don't need to unwrap. You need only to filter and then multiply this for this quantity. So we apply the prime RSS to this formulation, so we need to filter this component that is essentially the raw ionospheric component to find the lambda low and lambda height to optimize the terms Z, okay? And in this case, of course, you retrieve 2 times the ionospheric phase. You need to unwrap the results, of course, but the estimation seems to be quite good. The problem of this formulation, actually, is that for the filtering procedure is quite critical, because if you have a stronger non-dispersive component, the filtering procedure is not so effective. Actually, are critical, because this is the only simulation where you have, we use a deformation pattern of 20 centimeters that we add to the original interferograms, okay, to generate this new interferogram with this strong non-dispersive component. If you try, okay, to this formulation here, as you can see, to this interferogram, of course, you have some residues here. Is a problem connected to the fact that in the ionospheric phase component, you have also a full band interferogram. So you should tune, okay, the filtering procedure to compensate the non-dispersive component. So we essentially, even if you try to filter again this component, you find some artifacts. So it's very critical. So we propose to, starting from this formulation here, to reformulate essentially. We factor out essentially the factor Z, and to express everything like the first formulation. An amplification factor here as something to filter in the bracket. Okay, if we use this formulation here, okay, by using, of course, the same interferograms, so we need, of course, to unwrap something. So with this formulation, we lose, let me say, the advantage to avoid the unwrapping, but we need to unwrapping this because it's multiplied for a real number, okay. We use prime RSS to optimize lambda low and lambda high. We estimate essentially a new Z factor optimum, also in this case minus 48. So we optimize the amplification factor, and we retrieve essentially the ionospheric phase. And if we compare the two formulations, these two formulations, essentially the results are very, very similar, actually equal. Only in this area here where you have yes, a lot of noise, the amplification of the noise is different, so you have an impact of the noise in these two, different impact of the noise in these two formulations, so we have some differences here. So, let's move to the final remarks. Essentially, the prime RSS algorithm is very easy to implement because you can estimate lambda low and lambda high optimized once, because if you don't change the sensor, if you don't change the acquisition mode, you need to estimate once. And then a spectral filter is very easy to implement because, you know, it's a Fourier transformation and a narrow band filter. And seems to be robust independently from the formulation. About the phase unwrapping is a problem, we know. And in our view, that works with multitemporal analysis. A good approach is to use the multitemporal analysis, so to use, let me say, a more accurate algorithm, spatio-temporal algorithm to solve the problem of phase unwrapping, to reduce, let me say, the ambiguity connected to the phase unwrapping and the problem connected to the phase unwrapping. And yes, and there is a paper just submitted about this algorithm that we hope will be published as soon as possible, let me say. Okay, so thank you very much for your attention.
Thank you for your presentation. In your flow chart, I saw a problem, and maybe it's only in showing the flow chart and not in what you process. Yeah, maybe you go back.
It's not so easy. Here.
Yes. So you have the two images, and then you do the co-registration with refinement, and then you select the wavelengths, and so it looks to me like you do the spectral filtering for the co-registered SLCs. And this would be problematic because if you refine the co-registration, you change the spectra, so you don't have so nice spectra anymore, and in some cases this degrades a lot the result or the potential of the method.
We use the shift estimated with the pixel offset within geometrical co-registration.
Yes.
The problem is that you say that...
And this modifies the spectrum.
Yes, but we, after... okay.
And then to do spectral operations like interpolation or bandpass filtering are critical. So in some cases, this may be really relevant. So we always do the bandpass filtering or the selection of the two subbands before the co-registration. And then you can do the co-registration using the same lookup table.
Okay, you are suggesting me to estimate the low band optimize a high band before the co-registration, right?
Yes, to generate the two bands before resampling the data.
Okay, actually, I'm not focusing the problem that you are. Okay, you are saying that pixel offset you have a shift of the spectrum.
In the co-registration with offset field, you corrupt the spectrum.
Okay, but you can select
because
before.
You have spatially variable.
Yes, but you can select the low band and high band before.
Yeah, exactly. That's what I say.
Yes, but you can do this once. I say that in the final remarks. You can do before, of course.
Yes.
You select, then you can co-register. The value does not change because you just need to optimize the amplification.
The flow chart looks like you do this after the co-registration. That's just my remark. So I was right. You just maybe the flow chart is not so well showing what you do, but you do the right thing.
Okay.
From what you say, yeah.
Thank you, Urs.
Very nice presentation, thank you. I was wondering if you, first of all, in ICE, that's what we do. We usually do it before co-registration, and I agree with that comment.
Yes, but we do actually, sorry.
Great. One of the big challenges is unwrapping errors, actually, right? So I was wondering if with your nice innovative idea of going gradually amplifying the noise, have you tried to deal with the unwrapping errors too?
About the wrapping errors, I say that, yes, you working with the one interferograms, you cannot avoid to face with the phase unwrapping errors. Our suggestion is to work with the multi-temporal analysis. Of course, if you have some areas that are not coherent for us, in our view, it's not important because there are no information there. So we want just to, let me say, to filter out the noise, ionospheric noise from the coherent points. So a spatio-temporal phase unwrapping can help you to find a good solution of phase unwrapping, and then to filter out, from the interferograms, the ionospheric component. Of course, we cannot solve, actually there are several techniques maybe proposed in literature trying to solve on a single interferogram the phase unwrapping error, but essentially, if you have, this is a problem, we know. But we solve by using spatial-temporal phase unwrapping.
Hard to do in operation. in a live system that one acquisition comes, you cannot wait for future, for multi-temporal. But yeah, thanks.
Welcome.
Okay, thank you. I think we move on to the last one. Given by Ivana Zino, from the same group. Ivana. Talk is on atmospheric correction for multi-temporal Duza analysis, again with ERA 5 models.
Thank you so much. So, good afternoon to everybody. My name is Ivana Zinno. I'm a senior researcher at IREA-CNR, the same institute of Claudio. This presentation is based on the exploitation of Serra-based atmospheric correction for multi-temporal Duza analysis. We will discuss the performance assessment and the comparison with the ERA5 reanalysis data. So, briefly, the outline. I will present the motivation behind this work. Then I will present the followed approach, some, let me say, preliminary experimental results and conclusions and future developments. Okay, as David mentioned before, the atmospheric phase screen still represents one of the major limitations for accurate Duza products generation, especially in the context of operational ground motion services. In literature, there are a wide range of APS corrections approaches, of very different, based on very different methodologies. So from the one exploiting DINSAR data-driven techniques, the one exploiting external numerical weather prediction model data, such the one discussed in my presentation. And I read recently also a lot of approaches using deep learning and machine learning techniques to estimate APS, but in my opinion, the problem is that they are very dependent on a specific test site and are validated on a small, a limited number of interferograms. Indeed, we are interested in robust approaches suitable for operational context and validated over a large multi-temporal dataset. This is the reason why we're exploiting ECMWF reanalysis data. First of all, because they are global available and also easy and rapidly to access through the CDS archive. ERA5 reanalysis data are widely recognized in literature to be pretty effective to correct APS component, mostly the stratified APS component, because due to their very coarse spatial resolution of 31 kilometers, they are not able to, let's say, estimate the final spatial scale component like turbulence and mesoscale components. This is the reason why in this presentation we investigate the effectiveness of SERRA data, the recently released dataset of ECMWF, which is characterized by a 6-time final spatial resolution. In this slide, I summarize in these two tables the main characteristics of the two reanalysis pressure levels dataset. So ERA5 is worldwide available, while the spatial coverage of SERRA is on Europe. The horizontal spatial resolution is a big difference because 31 kilometers for ERA5, while 5.5 kilometers for SERRA data. Vertical coverage is more or less the same, and the other important factor is the temporal resolution, because ERA5 are hourly available, while the SERRA data are available every 3 hours. They are very easily accessible through proper APIs from the CDS archive. And so, back to motivation, the point of my presentation is assessing the trade-off between the higher spatial and coarser temporal resolution of SERRA dataset for DINSAR APS correction. Okay, this is the workflow of the methodology we followed. We first generated the DINSAR products through the well-known PIS-bus processing chain. Then we estimated the APS delay maps from ERA5 and SERRA data at the times closest to the SAR acquisitions. The estimation was done by exploiting the PIAP software developed at JPL. And we modified, obviously, PIAPs in order to handle and ingest the SERRA data. Then, and here I have to reveal the murderer, we calculated the SERRA time interpolated APS delay maps through a linear interpolation between the two closest SERRA samples, bracketing the SAR acquisition time, in order to, let's say, match exactly in time the APS state at the SAR acquisition time. Then we corrected the PIS-bus interferogram and displacement time series through the 4 different APS delay maps. So ERA5, SERRA pre-SAR acquisition time, SERRA post-SAR acquisition time, and SERRA interpolated. And then we carried out the performance assessment on both interferograms and displacement time series. Okay, for the experimental results, we exploited 2 very different test sites. The first is the Mountain Etna, is a relatively small scene of 60 kilometers by 50 kilometers. The sensor is Sentinel-1, and we used ascending orbit data because, as we all know, the ascending orbit is the more affected by APS because of the acquisition time, that is more or less on Italy 5 p.m. The observation period is more or less 7 years, so 350 Sentinel-1 images and 865 PIS-BUS interferograms used for the experimental analysis. The final resolution of these DINSAR products is 30 meters by 30 meters. The characterization of the site in terms of topography and atmosphere. This is a steep volcanic cone rising from sea level up to 3,300 meters. The atmospheric regime is essentially dry Mediterranean climate. And so we expect here a APS strongly dominated by the stratified wet delay component. The second test site is very different. First of all, it's a very large area of the northwestern Italy area. The extent is 360 kilometers by 270 kilometers. Sensor again, Sentinel-1, ascending orbit again. 9 years of observation period with 410 Sentinel-1 images and 1,141 PIS-BUS interferograms. The final resolution in this case is 80 meters by 80 meters. This site is very complex, both from the topographic and atmospheric characteristics. We have Maritime Alps, northern Apennines crossing the entire domain, a sharp transition from sea level up to peaks of 2,000 meters. The atmospheric regime here encompasses Mediterranean and continental regimes interacting across the Apennine ridge. We have strong land-sea humidity gradients, and this is a site considered a Mediterranean hotspot for extreme convective precipitation. Think about the Genoa flood of 2011-2014. So in this case, we have an APS regime strongly dominated by mesoscale and turbulent components, very differently from the first one. Let's see some experimental results. First of all, I show here an APS on an atmospheric interferogram relevant to an interferometric pairs in summer period. In summer, obviously, the APS is more significant. And we have the one generated with the ERA5 data at 5 p.m. Then Serra data sample at 6 p.m. that are the closest Serra sample to Serra acquisition time, which is 4:56. Serra at 3 p.m. and last on the right, the Serra interpolated interferogram. Two things to note. First, the, let's say, very finer and richer spatial variability of Serra data with respect to ERA5, obviously for the higher spatial resolution. And second, very important to me, the very rapid change in time of the atmospheric phase screen. So that means that it is very important to, let's say, photograph to catch the right atmospheric phase screen to apply to the SAR dataset you want to correct. And this is the interferogram correction. So on the top, the PIS-BUS non-corrected interferogram, and 4 corrected interferograms with ERA5, Serra at 6 p.m., Serra at 3 p.m., Serra interpolated. In terms of standard deviation reduction, the one performing better is the Serra interpolated. That is, anyway, comparable to the ERA5 one. Same, so I go fast, example over the northwestern Italy test site. Again, we have the 4 APS different interferograms. Again, we can notice such different in space and in time. And again, if we see at the 4 correction for the summer period interferogram, we can see that the best performance is given by the Serra interpolated at the Serra acquisition time. But let's say, give a quantitative analysis of this phase reduction. So here I show you the analysis of the interferometric phase standard deviation at different spatial scales. So what we did is extract from each interferogram a window of increasing size. We evaluated the phase standard deviation within each window, and we averaged this value over the overall interferogram dataset. So 865 interferograms for the Etna and 1,000 odd for the northwestern Italy test site. The results are pretty different. So let's go in order. Okay, look at first at the Etna test site. In this case, we have a range of spatial scales spanning from 15 kilometers up to 50 kilometers. The black curve is the original non-corrected interferometric phase. Then we have the blue curve, which is the one relevant to the correction done with Serra sampled at 6 p.m. That is very close to the original one, so I mean non-correction. Then we have the 3 lines of HIRA 5 in green, Serra at 6 p.m. in violet, and Serra interpolated correction in red, that are very close to each other, and so I think perform more or less in the same way. How can we interpret these results? In this case, in which you have that the dominating component of the APS is the stratified one, actually the higher resolution of Serra, let's say, doesn't make a big difference. Instead, the other site, so the graph on the right, you can see that after the highest line that is non-corrected standard deviation interferometric phase behavior, you have that both the Serra correction lines, blue and violet, are perform worse than ERA 5, despite the higher spatial resolution, and the Serra interpolated correction represented by the red line instead is the one that shows a benefit. So the message is that even if you have a very high spatial resolution, a better spatial resolution, the most critical factor is the matching in time of your correction with respect to the Serra acquisition time. Let's move rapidly to the displacement time series analysis. I show here some time series. This point, this pixel, is on the top of the volcano. On the top, you have the PSBAS non-corrected displacement time series, and then the 4 different corrections. In this case, in which you really are seeing, I think, just stratified APS component, the 4 correction performs pretty good, and they are all able to mitigate the seasonal oscillations that you see in on the top, that are typical, a typical behavior of the stratified APS component. If you go on a pixel on a flatter area, you see more noisy time series, and the best correction is performed by the Serra interpolated corrected time series. Same for 2 pixels on the other test site. In this case, you can see, I would like to let you note that in this case, the Serra correction at 6 p.m. Seems to add noise to the original non-corrected time series. And again, the one performing better is the Serra interpolated correction. Same results for another point in the Milano area. And also in this case, this is the final slide, we quantitatively assess the standard deviation reduction in the time series correction. So for the Etna test site, we are looking at histograms of the displacement time series, standard deviation, evaluated for all the coherent pixels of the scenes. In this case, you have that the black dashed line histograms represent the original non-corrected time series, and again, the blue distribution, which is relevant to the Serra correction at 3 p.m., so the more distant from the Serra acquisition time, actually don't correct. The 3 histograms relevant to ERA5, Serra closest sample, and Serra interpolated sample at the Serra acquisition time are more or less superimposed and mitigate, let's say, the stratified APS component. This result on the right is, let's say, a little bit surprising, because in this case you can see that the violet curve, which is the distribution of the standard deviation of time series corrected with the Serra samples at 6 p.m., actually degrades the results. So this, again, means if you try to correct let's say, a insert time series applying an APS time series which don't represent the real atmospheric state in the Serra acquisition time, you risk to add atmospheric noise, add noise. And in this case, we have that, let's say, the green distribution, which is ERA5, does its job, because reduce the standard deviation, the peak of the standard deviation of about 1 centimeters. That is what ERA5 generally does. And the red distribution, which represents the Serra interpolated correction, performs better, so outperforms ERA5. So some conclusions. The temporal resolution is a crucial factor for an effective APS correction, and a temporary mismatch correction can be worse than no correction. Moreover, the benefit of Serra's high spatial resolution is regime dependent. Obviously, I think that these are preliminary results. I would like to extend the analysis to more test sites with diverse topographic and atmospheric characteristics in order to have a very robust performance statistics. I would like also to perform further statistical analysis to better assess the impact of Serra's high spatial resolution, for example, variograms that actually are already running, but they are very heavy from the computational viewpoint for a so large data set, so they didn't complete. To explore, like David mentioned before, interpolation schemes beyond the linear temporal interpolation. And finally, this is a direction towards we are moving, integrate GNSS-derived tropospheric delays to constrain the atmospheric state at the Serra acquisition time, and also maybe improving spatial resolution. Okay, thank you so much, and if you have questions.
We have time for questions. Yeah, go ahead.
Yes, thanks for the talk. I was really curious about your last slide, because it looks like results get worse at 6 p.m., but they don't get worse at 3 p.m. Well, actually, the acquisition time is 5:15. Can you go like the 2 slides back?
Yeah.
So on the right, you see that it gets worse if you take the Serra at 6 p.m.
Yeah.
But it gets better at 3 p.m., while the acquisition time is at 5:14.
Yeah. Yeah.
So for one of them, it's just 45 minutes difference.
Yeah.
That's worse, and the other one is it's more than 2 hours.
Yeah, actually.
Do you think why is it?
Very good question. This is let's say, counterintuitive result, but in my opinion, the acquisition, the atmospheric phase screen at 6 p.m. 6 p.m. is a very particular moment of the day in which, let's say, the APS reaches maximum because you have that the solar heating drives the convective mixing to its maximum, and you have the peak of the spatial variability of APS. So, which is the point? Even if you are closest in time to the Serra acquisition time, if the atmospheric state between 5:14 and 6 is changed very much, you are applying a correction which doesn't represent the actual APS state of that time. And so you don't know, maybe in that 45 minutes, something very, a very big change in APS happened, and so you are doing wrong. Indeed, I think that if you look at these results in detail, they are very particular. You have that, the violet curve is Sarah at 6 p.m. and the blue curve is Sarah at 3 p.m. The red one is applying the correction with the interpolated data set between these two times and works very better. This is because by interpolating, you are capturing, you are doing the right snapshot of the atmospheric phase screen at the moment of the SAR acquisition time. So you are correct in the right way, and your standard deviation reduces. I don't know if I was clear. It doesn't matter how distant you are in time from the SAR acquisition time. What matters is that you capture the exact, the correct atmospheric phase screen. Did you get it?
Yeah, thanks. Well, I have a small follow-up, because if you're interpolating between the two, then the 6 p.m. should also influence.
Yeah, you interpolate the correction, but then you correct your time series. So you add or subtract your correction to your time series, and you are evaluating the standard deviation of the time series. So you are not interpolating the corrected time series. You are interpolating correction and then correct time series. And so you have a standard deviation that just depends on how good you correct. So how much you catch the exact atmospheric phase screen at this time.
Yeah, thank you.
You're welcome.
Ivana, looking at the scales, you're talking about centimeters. Just a few presentations ago, we talked about millimeters when we compare GNSS receivers.
Yeah.
Did you think about comparing the models directly with GNSS zenith delays? Then you have continuous measurements from the GNSS, no time, no question about interpolation.
No, I think that one direction towards we can move is use GNSS to, let's say, improve the correction that we are able to perform with the ECMWF data, which is the point. GNSS give sparse measurements, very precise in terms of zenith total delay and in terms of temporal sampling, because GNSS is 5 minutes to 1 hour, okay? ECM but are very sparse because we have a limited number of GNSS and also not with a global coverage, okay? So this is the drawback of GNSS. On the contrary, ECMWF data give you a global coverage, but with a temporal sampling that is quite coarse. So you can think about, let's say, jointly exploiting these two information measurements, and it is possible to do because if you see at the zenith total delay measurements given by GNSS, let's say the time series are absolutely comparable in terms also of dynamic with the ECMWF data produced one. So the direction towards we are moving are trying to exploiting both GNSS and ECMWF data to obtain a always better correction performance.
For the correction, yes, but back to the step in assessing the quality of the models and interpolation strategies, temporal interpolation strategies for the model. No?
A lot of work to do.
Straightforward to look directly on a GNSS time series and compare that to the model and the correlation functions, so to say. Yeah.
I think that there is a lot of work to do in this sense, that we have to understand which is to figure out which is the, let's say, the better methodology to use. Yeah. Yeah.
Thank you.
You're welcome.
Sorry.
Quick. Thank you, Ivana, for sharing. Speaking of the interpolation strategy, have you considered interpolating both ERA 5 and Sarah?
No. Anyway, ERA 5 is hourly sampled. So in this case, for example, we have that ERA 5 is taken at 5 p.m. and so it's very close to both the Sarah acquisition time. Obviously, this is a possibility. Obviously, this is a possibility, absolutely. The point, which is the point? The benefit, because if I see these results, I think, okay, I use ERA 5. Because from the complexity point of view, if I have to download Sarah at one time, Sarah at the second time, interpolate Sarah, and so on, I need to do 3 different processing. I just download ERA 5 at the right time, and I use ERA 5. So the problem is the benefit. For sure,
you can benefit high temporal sampling of ERA 5 and high spatial sampling of Sarah.
In space, you mean the spatial resolution? I don't know if Sarah data are based on ERA 5, and they use more measurements in order to reach a higher spatial resolution. So I don't know if this makes sense, honestly.
Okay, thank you.
I think so. Officially, we should now wait for 15 minutes and then discuss. But actually, my proposal is we start discussing right now, and still others could join us later. We have now scheduled a roundtable discussion on atmosphere, ionosphere, and phase closure. So maybe Francesco, you want to join us again? Yeah.
They're here. Maybe other people might.
Yeah. Good idea. So, do you have any more discussion points on the presentations given now? Proposals, questions?
Thank you. So I have a general question to this broad audience about how can we better do atmospheric corrections in regions where we don't have dense GNSS or we don't have GNSS at all. We do not have high-resolution global atmospheric models like the one that Ivana just presented, which exists only in Europe, or models that are only available for North America. So I'm thinking isolated places, let's say in South America, Africa, or parts of Asia. What can we do besides just testing whatever corrections like GACOS or ERA 5 and then assessing the one that works best just by just calculating the one with the less residual? Can we do better than that in these regions that are far from ideal, that do not have good atmospheric data?
Sorry, this was too long for me to note. Can you repeat in one sentence?
Sorry, I'm sorry?
I couldn't get the...
So the question is, in general, is many of these atmospheric correction techniques are targeted for regions that have good GNSS data, high-resolution atmospheric data. So I'm wondering what happens for regions where these things do not exist. For example, places in South America, places in Europe, places in Asia, where we are just working with these very low-resolution models like ERA 5. Can we still do better than just correct with these low-resolution models and check if it works, or that's it? Are there any other alternatives at this point after so many years of atmospheric research with INSAR?
Well, I think we have shown the spectrometers to work very well and do a decent job with Maris Modus and actually they get to the water vapor component pretty decent. They don't do the hydrostatic, but that's what the models do very good. But we seem to have forsaken spectrometer aspects and falling back to the models. But I want to, there's two different things here. I feel like there is the scientific curiosity in getting the very best out of the signal versus the thing that works for everybody. I think there are the global atmospheric models, and as shown already, they do a decent job. But don't look at the 10-kilometer scale or the localized scale. And that is, I feel like, an open area where it really depends on the local climatological conditions, and it's an active field of research. So I don't think that there will be a one-fit-all solution for that. But I do think that the spectrometer aspects showed in the past to be very promising, and we haven't really pushed it that much in that direction anymore. Of course, it's cloud limited, but still there's different types of spectrometers that can penetrate partly through the clouds and still provide a constraint.
Should we note that there's a recommendation to ESA looking into spectrometers again? Or I mean, I would like to add even low-resolution models are helpful when you have topography. So the resolution of the model is not everything. If they have mountains in it, still even a low-resolution model can help in correcting, of course, not the turbulent part, but the topographic imprint of the troposphere. We had the last talk, the discussion on high resolution models. Should there be done more specific work on that? I mean,
so one thing that so the weather model community, when they're doing the modeling for the atmospheric conditions, they're not looking at the differential type of signals. So they're looking at how well is the model doing at regional patterns. So one of the things that for us, for this community matters is the water vapor. And there are certain models that specifically try to do the assimilation of ground-based radar or NextRad stations, where you're looking at precipitation. That is not the type of models that we typically are targeting, but those are probably giving more of an observational constraint to the problem of water vapor. So I do think perhaps exploring which models in that domain might be suitable and trying to assess their performance, which should have more of an impact to the turbulent, to the wet component.
Particularly since where those are available, you get models every 5 minutes, potentially.
Okay, we have another question from Geert.
No, I just wanted to say that I agree with you, because I've been looking at local or high-resolution weather models in the Netherlands, just the predictions, and normally they are quite good at like predicting what type of weather you're going to get. But if you have like these convective systems, they're always wrong with the location. So for correcting for INSAR data, they're no use. So like I think like the Sarah 5 kilometer, I think that's more or less the best you can get. But maybe based on, for example, rainfall radars or something, you can make an improvement there. But I think it should come from observations and not from higher resolution models.
But one thing to consider when you talk about the precipitation radar, ground-based radar, it's a shorter wavelength that interact with the water drops. And that water comes from the water vapor in the air. So that means that water vapor, which is a signal that INSAR can capture, disappear, and then show up as a signal in a like Ka, Ku, or X-band, C-band ground-based radar. So they're looking at a different thing, I think. So in INSAR signals regime, they disappear and appear in the precipitation radar.
Yeah, I think that's true. But the key thing is you're putting it into the model, right? So it's an observation on the model. How do I get precipitation in the first place? For that, you need to have saturated water vapor to occur. So it's a physical constraint to the model, which many other weather models currently don't assimilate. So totally agree. It's not the same observation, but it's something that does constrain water vapor occurrence.
I want to encourage people to also ask questions or have comments about phase misclosure, because we do have to come up with a discussion for Friday. And otherwise, and recommendations. Otherwise, I'll just write my 5 favorite.
And I heard ionosphere come back already yesterday, so that's also under atmosphere, so feel free to chime in. I see France, you're putting your hand almost up.
I mean, I think for ionosphere, we're in a better place in some ways because there's better data-driven correction methods in place. I think some gaps that still exist include dual pole feather rotation correction. So a lot of the L-band systems will operate predominantly in dual pole mode. And so even though we're trying to avoid peak total electron content by picking ascending and descending node times around 6 a.m., 6 p.m., there is going to be feather rotation in places. That's beyond what the mission should get given the mission requirements. And so thinking about and revisiting methods for at least detecting and potentially correcting feather rotation in deprived data sets as dual pole data sets would be useful. Either using machine learning or using scattering modeling, et cetera. So there's probably some research that could be done to improve the amplitude quality, especially in the cross pole, in the presence of feather rotation. And then I wanted to say real quick, so ESA is having, I think, an ionosphere workshop this fall, which is really interesting. NISAR has a lot of ionospheric distortions in it that you can successfully correct, but you also can create a whole lot of information in the process. So I think we currently still treat the ionosphere only as a noise signal, but I think it's also a really interesting data source for potentially a new community of SAR SAR users that are interested in ionospheric parameters.
So we see more and more that the ionospheric corrections are embedded within the products and being distributed with it. We also have heard ESA talking about reprocessing data to the historical sensors. There are these tropospheric data sets that are out there. Is there any interest or need to see that over just routinely available? I know it might not be the holy grail, but if you would go with would it increase the accessibility for the community if there is an accessible correction where they would just download it and apply it to their historical sensor data? And I don't know how many people are still processing that, but there is a whole reprocessing activity ongoing, and the problems that we had in the past, they're still pretty much applicable there.
No, now it works. Okay, so only I'm trying to organize to wrap my mind around the thing of the closure phases, where we are, and I don't know. So in the past, the problem was for me, we only had Sentinel-1, basically. And then we were curious about L-band, and we got some ALOS 2, but these data sets were very limited because there were only a few acquisitions per year, basically. So it was very sparse and was hard to find, and mainly only on some places. And so it's like there was this, always at the Roselle meetings, I was saying, we need something. Okay, and now I think it's changed because with Saucom, NISR, maybe even the Agri-Roselle. So this side, for me, it looks like, okay, this bottleneck is no longer there, and we are more, I would say the problem now is to understand the data, so we have to look at them. I don't know, I see some people try to model things from more the physical perspective. I'm thinking more, maybe we just get the algorithms somehow, I don't know, but this is my impression somehow, that we, and I was forgetting, there's also biomass, like what Irena was saying. So we got even deeper down. And so the questions like that were like, there's this hope that L-band is better than C-band, and who knows, maybe the sensitivity is even less, or maybe in P-band it's even less, or who knows, maybe there's in some places it will be better because we go through vegetation, sometimes we lose sensitivity, who knows. So I think there are all these questions, and maybe for me this is the most, maybe it's difficult to convince ESA, I don't know, that this is the thing to be done. But like maybe we were trying, like in some, to add some algorithm development inside, campaigns or, I don't know, this would be where I think we are. I don't know what you think, or you think there's some gap in the observations yet still that we need to feel first and then we look at the data. I don't know.
Hi, Francesco.
Hi, Anesh.
I'm confused. What are you suggesting exactly? Can you clarify?
Okay, thank you. As simple as that. Like 5 years ago, I was thinking we are lacking data. So we only have Sentinel, and we don't know if we can recommend doing these things in L-band because we could not see this. But now, in my opinion, there's so many data. Now we are behind with interpretation, understanding, models, algorithms, filtering, and all this. This is my vegetation, like understanding the HHVV phase, why it's there on vegetation and not some. So this is my impression. Or should we still ask ESA for more campaigns, more ground-based SARs, maybe multi-frequency at the same time, because that's the only way we understand.
Yeah, I think ESA is mainly waiting now for, we have a lot of data, or we will have soon. We are now creating simulated data for Roselle, triggering some future studies. And what ESA now wants, actually, from the community, or expecting from the community, is your ideas for future studies, how to exploit, what we can see else in this data, what we can do, because this is something that has to be, has to be triggered by the community at the end. No? Yes. So not everything can go with the open call, right? Because there is a mechanism of an open call that people can suggest ideas for studies, but for bigger projects, if there are any particular suggestions from the community for something that should be still exploited or checked, this is something that I think ESA is waiting for.
Just to follow up on that, I agree that we are now in an era where we have a wealth of SAR imagery coming, and what I've found working with NISAR is that one of the hardest parts then is going and finding the in situ data. And there's things like the International Soil Moisture Network. There's so much historical data there, but there's not a whole lot going into the future. And so I'm not sure how to make this a recommendation, but re-engaging with the community that do larger scale collection of this sort of data and ensuring that they feel valued and are cited appropriately and included in the studies. Because when I've interacted with folks from that community, it does seem like there's a fear that they'll just be treated as data providers and not included in the analysis.
Maybe, okay, just a quick question, comment. For face closure techniques, what is your, your vision about the next steps? What is the weaker direction where we have to work to, I mean, is, I don't know, validation with what we, let's say, we claim to estimate, or new processing techniques, more advanced models, because okay, my experience, I spent a few years about this specific topic, not clear to me what we are going to measure. So what is the next step? Use L-band data to observe something similar that has been observed, or try to understand what we are going to estimate? So what is your opinion about this?
There's one
On the top, right.
There was first, sorry.
Hands up, hands up.
No, no, no,
There.
come back.
Oh, while we're sorting it out,
Irina hebt eine Hand.
in terms of Rowena's comment about ground truth data, so closure phase is, to me, is one of the most enigmatic physical process that I always scratch my head. And Francesco, he introduced a new way of processing, two references, and then there's a linear combination, some fudge factor, he didn't elaborate. And then maybe the assumption of deeper layer is weaker is not correct sometimes. So I was like, what? What does it mean? In that case, what kind of ground truth data would enlighten us? Do you have any thoughts? What might be useful to test it?
No, but the same problem seems to be, was in the backscattering thing, you know, this paper from, I always cite the same paper from Wolfgang Wagner, 22. So they also saw that sometimes you have apparently stronger backscatter from below. So it's like maybe you modeling, more advanced modeling will confirm and put all the pieces together, because we have to fit the data. We have to fit the backscatter, we have to fit the closure phase. So for me, maybe that's not a big thing. Like sometimes we have more backscatter from deeper.
Francesco, I have a related question. What do you have a proposal? What could be done to clarify that? What kind of instrument would one need? High bandwidth, Fourier analysis, tomography, whatever, to separate the scattering layers and to find out?
I'm just going to suggest something we were talking about earlier. One of my students is looking at C-band and L-band data over some of these regions, which are very specific areas where you see this rollover in backscatter as soil moisture increases. And looking at the wavelength dependence of it is something you can only do when you have a long time series, because you need to sample a whole bunch of different soil moisture states to see that. And this is already one of many reasons that promoting long missions that can give us those sorts of multi-year time series.
But with respect now to concrete recommendations to ESA for further studies, would there be a way to have we would have a very large bandwidth system, or do you think there is any technical experiment that could be done to validate that or simulate this behavior of different scattering volumes or layers in the...
No, I don't know. My original opinion was we have a lot of data. Now we should look at maybe NISR and Sentinel-1 together. And maybe it's difficult for ESA to have this perspective, but it's like, okay, let's look at this. maybe in preparation for Roselle and for the system of systems. Or,
but this would be a recommendation.
Yes,
Look at the data.
Look at the data
study,
that we have. Now we have
studies,
NISER.
looking at the data.
NISER, and we have Sentinel-1. Look at them together, time series together, and try to understand. We need models that fit the data. And I think Closure Phase already gave some push in the right direction, because now we are not understanding soils as simple surfaces. We already see the little 3, 5, 10 centimeters below. We understand there must be something like this. So we have, I think the physical model is improving because it's closer to reality. But we have to understand more vegetation, I think, and all the interactions and water in the vegetation.
Maybe. Okay, yes, then I would just jump in here. Yeah, I have also some recommendation. I would first, I mean, as you said, vegetation, I think for me it's very important to have studies concerning to see how we can tackle vegetation in order to estimate soil moisture. And there could be very, very different things. I mean, I'm advocating polarimetry, right? There's one part that you could potentially do. Yeah, I think it's great. Also an L-band, so also Roselle could be very helpful. Polarimetry could be also very helpful for ionospheric studies, right? In order for correction, we have now had with biomass a lot of success using polarimetry, right? In order to correct ionosphere, which will be not possible if we don't have polarimetric L-band systems, right, which in order also to try to correct it better. I mean, probably NISER, I know NISER has also a lot of problems. They will tackle it differently, clearly, but polarimetry would be very great too, I think, in order to tackle it a little bit, so you probably have different approaches. So that's one thing. I think ionosphere would be great to have polarimetry. For vegetation, it would be great to tackle it also with a closure phase. I think also the combination, so I have a presentation on Thursday which shows also that using the combination between DINSA but also baselines, right, in order to separate volume from ground could be very, very helpful. This is also a combination of zero baseline to spatial baseline variability could be very great. And the third next thing what I thought would be very great too. So for biomass, what they started now to do in order to have some ground measurements about forest height, they have established called geotrees, where they have super sites worldwide. They are collecting regularly ground measurements, and if something like this could also be established for the soil moisture community, could be really great to have regular acquisitions and to compare them with the acquisition that we have in a moment. Yeah, this would be my recommendations.
As you said, we have now a great source of data and loop closures in different wavelengths, in different polarizations. And so the question is whether the technique is mature enough to think of some global products coming from these misclosures at this point. We have the soil moisture global data coming from backscatter, from both Sentinel data, and also the NISER is quite prepared for that. What about the from loop closures? I mean, the technique, do you think is, I mean, at that stage now to think of the global soil moisture data or vegetation dynamics data from loop closures or not? Yeah, I mean, I'm just asking whether I mean, given the huge number of, the huge source of loop closures coming from different wavelengths and different polarizations, are we at the stage that we can think of generating some systematic global products, for example, from soil moisture, using the loop closures, or some maybe vegetation indices from the loop closures or not?
I don't think we're at that stage yet.
I don't know. So probably I would say we need to merge with backscatter. We need a fusion step because there's a lot of, I think, synergy or complementarity. And I think we need to merge with backscatter. We need a fusion step because there's a lot of, I think, synergy or complementarity. And I think we need to merge with backscatter. We need a fusion step because there's a lot of, I think, synergy or complementarity. And I think we need to merge with backscatter. We need a fusion step because there's a lot of, I think, synergy or complementarity. And in the areas where we looked, around the Mediterranean, the results are good. So I would say one should scale slowly, probably upscaling, yes, try a bigger region, and then, yeah, I don't know. Maybe in time we have problems, yeah, because I said like 3 years I was able to do something, but then coherence is low. But considering, I don't know, but I did something, there's something else. Elizabeth was doing something, you know, there's 3, 4 people or groups who have tried this. It's very young, but I think it works somehow, so it's not so incredible. One should think about like how to step by step reach some more maturity. And for me, the crucial step is merging with backscatter, because if you think to have an interferometric product everywhere over a forest, you know, and at C-band, it's not going to work. So it's crucial, the integration with backscatter for me.
Maybe I'd like to come back to the ionosphere. Was there another comment on this? Ah, yeah, sorry. Yeah.
I wonder if we could check the soil moisture models by a laboratory experiment. We fill some box in a controlled way with sand and stones and moisture sensors and add some water. And then we see if the model fits.
They definitely do that. There's actually this wonderful image in a paper from the 80s showing a giant radar dish pointed at a giant sandbox. I think we might be getting to the point. I mean, I work with people in Florida who have a radar they point at the ground and they take it out in their fields. They've had some trouble getting it to match the observations from what they know are going on the ground. But yeah, I think that is something where we should always have more of it.
Many comments?
Hello. May I have just such a request of the end user of the data? I am working in geology, and we are monitoring landslides and subsidences. And there is one case where is a big mine, and with C-band we can really, by permanent scatterers, monitor just some points. And this is subsiding quite quickly, and I was experimenting with ALOS, and ALOS 2 was made public actually already. So there is quite a nice stack of data. But first thing that I found it in Vertex, for example, but also there is gPortal. And when I downloaded the data, I was using Snap and it could not read them. Yes, that was one point. And then would be great, I was processing in another software, if there is something for end users already for L-band to correct the tropospheric and ionospheric influences, that it is not just on the level of science, but really provided in Snap in new version, for example. Thank you.
I think, can somebody comment on SNAP? I think I just heard ESA is integrating the ETAD product. Is it true? Somebody, Christoph?
We are already supporting ETAD.
It
yes.
is supported,
Yeah.
So, at least partly. I'm not aware about the split spectrum approach for the ionosphere, but I think ESA is on the way in supporting that in the SNAP software.
Yeah. So I briefly want to go back to your point. So if you're looking really locally at the mines, probably you can get away without doing the troposphere or the ionospheric corrections because it's very localized motion. Once you start looking at bigger scales, that becomes more of an issue. But I think you're bringing up a topic where perhaps you want more accessibility within the SNAP framework for tropospheric packages or for pre-computed corrections that are already there. So I think that is something that we can take away and provide to ESA as a recommendation, because within Europe it's a pretty broadly used package, and yeah, so we'll take that into account.
Yes, I have a small comment about uncertainties. So I studied geodesy, and they say if you give an estimate and you don't give the uncertainty, then you're not a real geodesist. And therefore, I wonder, when I do soil moisture inversion, how uncertain the estimates are, and for what ecosystem maybe the estimates are usable, and for what ecosystems the estimates are not usable. So I think uncertainty quantification could be very important for global operational products, and yeah, comparing it to some reference, possibly.
Ionosphere. Maybe a question to American friends. Since we have the opportunity having C and L band in Europe, you have the opportunity having L and S band. Are there already experiments planned or something combining that for ionospheric estimation reduction using this huge frequency difference? Do you see a way there that we could prepare or learn in Europe?
I mean, there's opportunities with the L and S band observations in several ways. So one downside is we at NASA hold the L band data. The S band data are held by ISRO, but should come out, I think, later this fall as well. So there is locations where there's L band data and S band data acquired simultaneously. So you could use that for improved split spectrum processing with the larger frequency separation. You would expect about a factor of 10 improvement in phase accuracy. But you also have potentially quad pole in one and dual pole in the other, so you could start studying dual pole implementations for feather rotation correction. Another thing that people use a lot for looking at ionosphere is looking at azimuth shifts. So there have been approaches in the past that look at these distortions in azimuth to sort of invert ionospheric gradients from it. But the problem there is that you have other things potentially on the ground, like if you have a glacial motion that also causes geometric shifts. So there's an ambiguity there. But if you have L and S band data, then you could actually use the shifts again, because you get different amounts of shifts in L and S band, but the geophysical shifts will stay the same, so that you could resolve these ambiguities. So I think it's in some places over India and in places where the L and S band data are available, it's a really nice sort of laboratory to study ionospheric correction and different approaches, and maybe come up with recommendations for future implementation of correction methods that may use amplitude, phase, polarization sort of jointly for correcting the data.
And for operation, this was discussed yesterday, how rows L will be phased with respect to Sentinel-1, close together.
Yep.
Only then would we have the chance for maybe perfect atmospheric correction, or put them apart and they are independent.
And then there's also P-band, not to forget. In P-band, you get some interesting artifacts where you can't really think of the ionosphere anymore as a thin layer, which we often do in L-band and in C-band. So I think you learn a lot also about ionospheric structure in the process while you work on these techniques. Yeah, so I think having simultaneous acquisitions at the two frequencies, multiple polarizations, both of them interferometric, opens up a really nice opportunity to study different methods.
I disagree. So totally disagree. So I think if you do this, it doesn't bring anything. So if you have like so I think it's a bad idea. Let's explain why. Simultaneous observation of C and L band. Then you have a super good ionosphere, But basically, you already have C-band, which is not so affected by the ionosphere, and it's limited by the troposphere and everything else. So it's maybe to do a study, yes, to study something, to learn something about the ionosphere, but like in an operational case, I think there's nothing, you're wasting a satellite. Huh? So you want to sample the troposphere at 3 days later, instead of having a simultaneous sampling of ionosphere and troposphere, I mean, L-band and C-band in 1 day. So I don't think I think it's a waste of, 3 dB of troposphere mitigation. You estimate a super good ionosphere. You could correct very well the L-band, but basically you already have the sample at C-band. So.
Yeah, you could, but you could get it even better in C-band, and you gain only a square root of 2.
C-band, we're already at centimeter level.
Yeah, depending on the situation.
We have troposphere, which is dominating. So, no, bad idea. I don't know. Convince me. Prove me wrong.
Howard.
So I'm glad to hear this diversity of opinions. I think it's a good thing. But in terms of thinking about, what kind of a recommendation to ESA that ESA could actually do something about, there have been a series of meetings for a good number of years, and I think, Michael, I think you have attended these in terms of international cooperation and coordination of sensors and systems. And maybe doing something like that on a little bit higher level and those meetings have been kind of small, 20, 30-ish kind of people, the few that I attended. But something that's more on a regular symposium where this is one of the main themes. You could address these scientific issues for sure, but there are probably ways to better mechanizing data access and availability and sharing. ESA might be able to have a good discussion with our colleagues in India who are sitting on all this S-band data that's not particularly available at the moment. But between in the US, we have NISAR, and in ESA, you have Sentinel, and you have Biomass, and you have your other planned mission. And the Japanese are running ALOS 4, and even though I really can't say this being from the US, the Chinese have the Lutan series, and there's many, many of these. And if there was a better coordinated way to get these instruments to play together and at the very minimum, have everybody just agree to let data out. As you know, data providers have various reasons for not doing that, and some are better than others. But it would be nice maybe to have a more organized worldwide group, I think, that could kind of coordinate that. And I think we could probably do a lot of these individual studies and things that people are talking about if we have more access to more different kinds of data and give you insights into what to do going forward.
Maybe to Francesco's comment, I don't disagree with you. I'm not suggesting to build missions that are multi-frequency just for the purpose of ionospheric correction, but in this case, we have the data, right? So, I mean, there's data available, and it's a really nice way of studying different approaches and techniques. But, more use the data that we have, not necessarily suggesting multi-frequency observations just for the purpose.
No, but even a multi-frequency phase would be nice to study something. I mean, Roselle Sentinel-1, maybe, I don't know, close in how it's called, not formation, but, there's close formation. But the general thing is like the double of the spacing of the observation, the double coverage in time.
No, but we don't talk about a decision. We talk about learning what's physically going on in the signal, and then the simultaneous observation, obviously.
We were talking about the large volumes of data. I mean, I don't see ASF replicating the Sentinel-1 next-gen, all the future missions on top of what is already there, potentially. Similarly, access to NISAR data through the full replicating of the archive is also not going to happen. I don't know, the topic of making the data very easily accessible across the Atlantic, Pacific, accessing JAXA data, etc., also a higher level conversation to ensure that the community is not bottlenecked by just trying to read a data file or do even analysis on it. I think currently we're in a luxury position in the US that the archive is being mirrored, but I don't know if that is sustainable at the rate that we are acquiring and new missions are onboarding. So that's perhaps also something that I would recommend, at least to ESA, to foster that again in the SAR coordination level and see what that looks like in 5 years, 10 years, and what is attainable.
Yeah, there is a, at least used to be, is it an annual or biannual SAR coordination workshop, which so far has focused very strongly on trying to coordinate the missions themselves and acquisition plans. But I think it might be more successful to coordinate on data sharing in a way where we don't have to duplicate data. So, you know, stack catalogs, discovery mechanisms, and just an understanding and a broader willingness to share the data sets that are available with the science community in some sort of jointly discoverable space. It could be a recommendation for this workshop to add a component on data sharing or data coordination in addition to mission coordination.
We have reached the end of our allotted time, unless someone has a final comment they'd like to make.
Thank you, everybody.
Okay, so we have this session. Thank you.
I will write some stuff down on my phone now.